Wisconsin in January, which is a long story, but not a story for this venue. So this is me. Before I want to give you a sense of what the research I do before I start going into the lecture. But I also wanted to say that I'm very excited to be here because I was in Moscow 38 years ago. So this is my second visit to Moscow. I was here in 1979. And that means that even relative to those of you who were born in places that were part of the former Soviet Union, I have experienced something you have not, which is Soviet communism. And I will tell you that my reaction to that visit, which was utterly fascinating, was not, wow, the food is really good, I should come back and have more, which is kind of my reaction this visit. So that at least has changed. But I would be very curious, if any of you are interested and are from countries that were in the Soviet Union, I would be very interested in talking to you about how you think about that past, and what you know about it and what you think about it. Because, you know, we should talk about your papers too, for sure. But I read a lot of books. There was a whole genre of literature in the United States of people who had left the Soviet Union, people who had defected, and then they would write a book to help support themselves. And I read a bunch of those books in high school and college. And so I have ideas about what it was like, but I would be very curious to hear what people think it was like who have grown up in these places and have living memories of their parents and so on. Anyway, point number one, I'm delighted to be here. Point number two, who am I? Well, these are things I work on. So I did my doctorate at the University of Chicago. Petra Todd, who you will hear from on Friday, was there at the same time as I was. She started a little bit after me. We both worked with Jim Heckman, who of course is the great presence that overshadows this course, right? This is his center in a very important sense. One time when we did this course in China, we had as the background for the projector, we had a picture of Jim. And so he was kind of always there looking over us. That was a very intense formative experience, working with Professor Heckman, and one I greatly value. There's many stories to be told after beer about that experience, but the value added was very high. And Heckman students are shaped by what he was working on at the time they were students. So prior to my time was the fertility period. And so my soon-to-be colleague Jim Walker at Wisconsin worked with Jim during the period when he was studying fertility and economic demography and doing duration models of, you know, time to birth and so on. That's a different set of work. Jim being Jim, he then moves on and does something very different, which is job training programs or active labor market programs. That was the period when I interacted with him, when Petra interacted with him, when Ed Bittler still interacted with him. Then he moved on after that to the early childhood period, right? And so now you have people like Flavio Cunha who know all about models of human capital development at young ages. That's related to but distinct from what we were working on when I was there. So my career has centered on applied econometric methods for evaluating active labor market programs in particular. So I have a set of papers on social experiments, their strengths and weaknesses. My first paper with Heckman in the Journal of Economic Perspectives, still, I think because people teach it, still cited pretty often, was on assessing the case for social experiments. And it was part of a pair of papers, one of which was sort of pro-experiments, one of which was sort of not anti-experiments, but a bit more skeptical. That was our paper. I think our views have held up well, and I think they define a nice middle ground between the rah-rah cheerleading social experiment papers and the very negative papers by people like Angus Deaton, who I think sometimes go too far. We did a lot about non-experimental methods, especially matching at that time. And I will be talking in the second part of the lecture about the Smith and Todd paper that Petra and I wrote during and after graduate school that was very important in the literature on matching in labor economics. Subsequent to my time in graduate school, I've written papers about regression discontinuity designs with Dan Black and others. And I've done a bunch of substantive papers about active labor market programs, applying these methods. I have a secondary literature which actually goes back to pre-Heckman on college quality and university quality. So how much does it matter for your labor market outcomes, whether you go to a good college or a bad college? How do you measure what's a good college or a bad college? Those papers I've continued to do. Most recently, I have a paper in the Journal of Labor Economics earlier this year with my student, Nora Dillon, who is now at Amherst College. I have done a set of papers on statistical treatment rules, and we'll be discussing statistical treatment rules in the first part of the lecture. A statistical treatment rule is a rule for determining who to treat, who to let into a program, who to assign to a particular service based on a statistical model estimated using data from earlier cohorts in the program. They're interesting. We'll talk about those. And finally, I have some work. I haven't done much on this lately. I'm hoping to get back to this a little bit at Wisconsin, because there's a tradition of working on this at Wisconsin, on what the US literature calls performance management. So performance management is essentially, what to call it? You know, there's an old literature from the 20s and 30s called the socialist calculation debate. And the idea of this literature was to say, in a planning regime, how can you mimic the allocational properties of the price system, right? And so Hayek was on one side of this discussion saying that you really can't do it, that there's so much distributed information that can't come to the center because it's held by agents away from the center, that the price system is necessary to incorporate all that distributed information in the allocation of resources. The counter side were people like Oscar Lange, who were saying, no, there's ways under planning that you can mimic the allocation activity of the price system of getting resources to their most valued use. Performance management is kind of that. But in a much kind of reduced, less grand sense, right? So if you have a job training agency in the US, these programs are very decentralized. There's a lot of local agencies. They get money from the center. They're supposed to do good things with the money. How do you know whether they've done good things with the money? How can you provide them with an incentive to do good things with the money? Well, one thing you can do is you can measure what they accomplish and reward them for what they accomplish. The problem, of course, is that what you would like to reward them for is value added, the impact, to use the jargon of the Freeman effects. You'd like to reward them for the difference in the employment outcomes of the people they serve between the world where those people get served and the world where they don't get served. But that's very hard to measure, right? And it's very hard to measure quickly, because you have to wait around for those outcomes to realize themselves. And so performance management is kind of tools, most of which I would argue are abject failures, tools for attempting to do that quickly and cheaply, to find proxies for the thing that you actually want to reward, and to reward the proxies. I think I'm the only person in the literature who sees a link between that and the socialist calculation debate, but I think that's really what it is. It's really getting back to this question of how can we use mechanisms other than a price system, because for these job training programs, there's sort of no way to bring in the price system. How can we use alternative mechanisms to try to get resources to the more effective local agencies? So that's kind of what I work on. This is partly to give you an idea of, you know, should you chat me up during the break? And if so, what should you chat to me about? As everybody said last night, a lot of the fun of these courses for us is talking to the students, meeting the students, hearing what they're working on. So don't be shy, right? Talk to us. We actually want to talk to you. That's why we're here. We do get paid a little bit, but not a lot. And we get well fed, as we saw last night. But it's also very easy for us to just stand around and talk to each other and to gossip about the job market or to give sage advice about how to be a good PhD student and blah, 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 blah. So you have to sometimes actively dissuade us from just talking to ourselves and gossiping. So don't be shy about doing that. Okay, so there's going to be 2 lectures, and the fact of the matter is that each of these lectures could easily take 2 hours if I gave it and talked slowly, as I'm trying to do, since I know most people here are not native speakers. So you're going to get parts of the 2 lectures with a break in between. And I'll try to sort of do the highlights. It'll partly be guided by your questions, and you should feel free to raise your hand. You should even feel free to raise your hand if I've put a term up that you're not familiar with, or if I'm speaking too quickly, or whatever. There's no value to you in sitting there watching slides go by if it's not clear what I'm trying to say. And I'd rather go slowly and make some of it clear than go quickly and have it not be clear. So I'm going to talk about some notation that will be familiar to most of you. I'm going to talk about parameters of interest. Most of that will be familiar, but it's kind of the necessary groundwork for what we're going to do. Then I'm going to do a simple but useful model. One of the underlying themes of the lecture, and I think of this course more generally, and I think also of Heckman's work more generally, is that there's a very important interaction between the economic theory, the institutions, and the applied econometrics. That those things are most powerful when they are combined together. And so that you're not just doing a theoretical exercise with a sort of empirical afterthought, that you're not just doing empirical work that is atheoretic, that is not guided by an understanding of the relevant behavioral theory, the economics of the problem, but also by the institutions. Institutions are important. And indeed, as you know, institutional variation is often critical for identification in a treatment effects context. It's critical for generating the variation in the probability of treatment or the nature of treatment that we use to try to back out an effective treatment. So I'm going to do this simple but useful model that's going to, I hope, highlight this general idea that theory is useful for applied econometrics and also motivate and frame the rest of the discussion. The bulk of this lecture is then about treatment effect heterogeneity and how to think about treatment effect heterogeneity. And the fact of the matter is that most of the papers that you will read, even now, 90% of the papers that you will read, implicitly or explicitly assume that the effect of the thing that they are estimating is the same for every unit. Excuse me, you will read papers about the effect of blah. Whenever I see the phrase, the effect, I cringe, I shake, and I say, no, 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 no. Treatments have heterogeneous effects. So part of what I'm going to try to do today is to make a pitch to you, to have that same reaction. When you read a paper that talks about the effect of the minimum wage, or the effect of job training, or the effect of democracy on countries, that you will say, wait. There's heterogeneity here that I should think about empirically and theoretically. And so I'm going to try to make that case to you, that that's important, and talk about different ways to incorporate that heterogeneity into the applied work that we do. If there is time, which there usually isn't, I will say some things about external validity. I will say some things about general equilibrium, which I think is something that remains under too little incorporated into the literature on treatment effects. Almost all of the treatment effects literature, 99%, is partial equilibrium. Almost all of the standard strategies that we think about, experiments, regression discontinuity, matching, diff and diff, all the stuff that dominates the literature, those are all partial equilibrium strategies for estimating the effects of treatment. You might imagine that many treatments have general equilibrium effects. How should we think about that? Probably we won't get to that, but it's there, and you can have the slides later for your use if you like. All right, notation. So this is the Mill, Frost, Fisher, Neyman, White, Rubin potential outcomes framework. So some of you might know if in certain parts of the statistics literature, this is called the Rubin causal model. Our leader does not get along with Mr. Rubin, it turns out. And mutually, right? Mr. Rubin doesn't get along with our leader either. In other parts of the statistics literature, this is called the Neyman-Rubin model. In Heckman land, back when I was a grad student, we called it the Fisher-Neyman-Roy-Quant-Rubin model. My contribution was to note that, in fact, there's this poem by Robert Frost called The Road Not Taken, which arguably anticipates Fisher-Neyman-Roy-Quant-Rubin. So I added Fisher, and then another person whose name I don't remember at a conference that I saw had discovered a quote from John Stuart Mill that in fact seemed to anticipate this notion of potential outcomes. And so now I call it the Mill-Frost Fisher-Neyman-Roy-Quant-Rubin model. Roy and Quant are, of course, famous economists from the mid-century, mid-20th century. And Roy, of course, is Roy of the Roy model, which is Mr. Heckman's favorite paper. All right, so Y1 is the outcome in the treated state, Y0 is the outcome in the untreated state as traditional, and these are things that we imagine as being there even though only one of them is going to be realized, right? Each unit is either going to be treated or not treated, but we can imagine in each case a counterfactual world. And I've heard a claim from a philosophy person that economists use counterfactual in the wrong way, or at least not the way that philosophers use it. It's our way. We can imagine a counterfactual world in which the person is not treated or is treated. And the treatment effect for each unit is the difference between their treated outcome and their untreated outcome, only one of which we observe. I'm going to use D as an indicator for participation in a program. This is a Heckman notation. Other traditions use T or S or R. I'm going to use R as an indicator for randomization to the treatment group in an experiment, because I want to distinguish that from participation. As I said, the treatment effect for unit I is the difference between the untreated and treated outcomes for unit I. I'm going to call that beta sub DI. In the common effect world, which dominates the literature, you take off the I subscript and you try to go after beta D, the common effect of the treatment. Substantively, when does that make sense? I would argue almost never to assume a common treatment effect. Where does treatment effect heterogeneity come from? Well, I think it's helpful in thinking about that, and I think it's helpful to think about that when you're doing empirical work, to think about why might there be treatment effect heterogeneity in my context? Where would it come from? To distinguish two cases. One case is a case where we represent the treatment by a binary indicator, but in fact, the treatment is not binary. Right? So if you think about this literature in political economy that tries to estimate the treatment effect of democracy on, say, per capita GDP, right? There'll be a binary treatment variable there. Is the country in this period of democracy or not, coded as 1, 0? But what's democracy, right? No, this is a hard measurement question. There are some countries where it's very clear, right? North Korea, no. Not a democracy. It has democracy in the name, but it's not really democracy in the way anybody would think. England, that's probably a democracy. They've had a parliament for hundreds of years, blah, blah, blah. But there's other cases where, okay, we've got to come up with a criterion that defines whether this country in this period is a 1 or a 0. You think about a country like Venezuela, right, which was, most people would have said it was a democracy through the 70s and 80s and 90s, but then, things kind of went sour. At what point do you change the 1 to the 0? Right? That's hard. And so in those years that are on the margin, the notion of democracy that is embedded in your 1-0 coding is different than it is for North Korea, right? Which is very far from the margin in every period. So you have a heterogeneous treatment. Even if you think about the countries that probably everybody would code as a democracy, they're different. Some of them are parliamentary democracies. Some of them are things like the US with different branches and da-da-da-da-da. Some of them are multi-party. Some of them only have 2 dominant parties. Japan, in the post-war period. One party won every election for like 40 years. But people would still code them as a democracy, even though one party ran everything for a very long time. Right? So that's an example of a case where the treatment that you have made into a binary indicator is in fact itself heterogeneous. We wouldn't necessarily expect the same effect of US-style democracy on economic outcomes as we might expect from French-style democracy on economic outcomes. Another example here is job training. I try not to use job training for every example, but it comes naturally to me. That's a lot of what I study. Classroom training and occupational skills is provided by many job training programs. But some people are getting trained to be welders, some people are getting trained to be hairstylists, and some people are getting trained in Microsoft Office. Right? In many analyses, all those people would be coded as treatment equals 1, and the people who just got job search assistants and got nothing would be coded as treatment equals 0. We might not expect the same effect on economic outcomes of being trained as a welder as being trained as a hairstylist. But then we think, okay, well, let's code up everything. Let's have a multi-arm treatment with 15 different arms. One for hairstyling, one for welding, one for Microsoft Office, one for this, one for that. That has a couple problems, which is what leads people not to code up every possible course you could take separately. The first problem is your sample sizes get way smaller, right? Because probably you're not training all that many people to be welders. And secondly, you have introduced yet another selection problem, right? If you code all the different kinds of classroom training as just a 1, then you have to deal with selection into getting any sort of classroom training. If you decide to study the effects of all the different flavors of classroom training, then you now have to deal with the secondary selection problem of how come some people get assigned to study welding and some people get assigned to study hairstyling. Right? That's another selection problem. Maybe you don't want to deal with that. So there's a question, and I've never seen anybody write a paper about this, but I think it would be an interesting paper to write, on optimal treatment differentiation. Right? What features of a context determine how finely you want to define the treatment? So I've just outlined 2 of them. One is the sample sizes available. The other is how well you understand the process of selection into the finer treatments. But implicitly, studies are addressing this, and usually it is just implicitly. Usually there is no explicit discussion of why the researcher decided to have 2 treatments, or 4 treatments, or just 1 treatment in their given context. They just state it. They announce rather than defending. One of my frequent criticisms about papers, especially student papers, is this whole business of announcing instead of motivating. Right? Don't just announce all your assumptions. I'm glad you know what they are. It's important that you know what they are and that you tell the reader. But explain to the reader why you think they're reasonable to make in your context. Right? Oftentimes, students in their papers will put down assumptions that seem to me completely implausible in their context. They'll just say, well, for simplicity, I assume blah. And blah is completely implausible, in my view. And there's no argument. Maybe there's not even that for simplicity. They just say, I assume blah. It's like, well, why? Tell me why. Make a case. Why should I believe blah? If I shouldn't believe blah, then make a case as to why it doesn't actually matter very much for the results that you've assumed something that's completely implausible. Anyway, that's another thing. So one reason why you might have treatment effect heterogeneity is that the treatment is actually itself heterogeneous. Even though you coded it as a 1, 0, actually there's 15 treatments and you collapse them all into the 1. The other reason that treatment effects might be heterogeneous is that units might respond differently to the identical treatment. So a common context where treatments are themselves identical is when we have budget set treatments. So these come up in a lot of contexts of transfer programs, taxes, and so on. Right? We change, let's say we change the implicit tax rate in a transfer program. Right? We change the rate at which the benefits are clawed back as the recipient has more earnings. That happens to everybody. Everybody gets the same treatment. The budget set used to have this slope, now it has this slope. Nonetheless, we expect people to behave differently in response. Why do we expect people to behave differently in response? Well, one reason might be that there is some unobserved factor that yields differential responses. So people who are receiving the transfer might have different opportunity costs of work, right? Some people may be at home caring for a sick relative. Other people may be at home playing video games, right? If we make it more lucrative to work, you might expect that the video game people will respond at the margin. The people with the sick relatives, not so much, right? If you don't observe people's opportunity cost of working, then all you see are heterogeneous responses. But that's the underlying mechanism, is that there's heterogeneity in this example in the opportunity cost of work. Thinking about, right, when you're setting out to write a paper that evaluates this change in the slope of the budget set that comes from a change in the implicit tax rate, thinking about why there might be heterogeneous responses, right? Thinking about each individual's decision problem and which aspect of that decision problem are likely to have substantively important I subscripts, right, is very helpful in thinking about how to go about your analysis. It's helpful in thinking about what data to collect. If you're in a situation where you get to decide ex ante what data you're going to collect, thinking about which variables are likely to predict heterogeneity in the treatment effect would be very valuable. Well, how do you make those predictions? You make those predictions by thinking about the model and the institutional reality, right, and how those things go together. So, in my paper with my student, Habiba Jabari, who teaches in France now, she is originally from Algeria, and as a result knows French, and married a French guy, also an economist. In my paper with her in the Journal of Econometrics, we distinguish between what we call systematic heterogeneity in the treatment effect and idiosyncratic heterogeneity in the treatment effect. So systematic heterogeneity is heterogeneity that is tied to observed characteristics. So in my example, if we observed people's opportunity cost of work, then that would be a source of systematic heterogeneity. If we didn't observe it, then it would be a source of idiosyncratic heterogeneity. So which parts of the variation in the treatment effect are systematic depends on what data I have on the variables that generate the heterogeneity in the treatment response. Questions so far? You've been very thoughtful and quiet. I only know two people's names, so it's I could call on people, but it wouldn't be random. One person in the room actually took my undergraduate econometrics class, which I think is super cool as an exchange student. So, and yet they're still here. So there you go. That's some sort of recommendation. Why do we care about treatment effect heterogeneity? Why doesn't it suffice to know the common effect, or to pretend there is a common effect, even if there is not? One reason is oftentimes we'd like to understand program participation, right? In the US, there's a big literature. Lots of programs in the US are voluntary. There's an eligibility rule. This is the case for job training. You know, you must have earnings below a certain amount, or you must be receiving certain transfers. But many of the people who are eligible never show up to get the job training. They don't think they need it for whatever reason. Understanding that choice, understanding take-up, as it's called, of programs, is interesting. And presumably, treatment effect heterogeneity is part of why you get take-up heterogeneity. Sometimes treatment effect heterogeneity can help you understand how the program works, the mechanism by which any average treatment effects come about. That's useful to know as well. And I think that'll become clearer when we see this little model I'm going to put up. We might be interested in the effects of programs on inequality. Right? A program that has a high average treatment effect, but which makes some fraction of its participants worse off, well, we'd like to know that, right? maybe we can better target, that's the last one, the program, so that the people for whom the treatment effect is going to be negative don't end up participating. All right, so this gets us back to the statistical treatment rules. Statistical treatment rules exploit systematic heterogeneity in the language of Jabari and Smith. All right, statistical treatment rules say, okay, let's interact the treatment indicator with a whole bunch of covariates, usually chosen in an extremely ad hoc and atheoretic way, but that's what they do. And then let's predict the treatment effect of individual units based on their observed characteristics, and let's try to get the ones with the big predictions into the treatment and get the ones with the bad predictions not into the treatment. That's a statistical treatment rule. If you can make that work, and there's lots of reasons why that's hard to do, if you can make that work, you can improve the efficiency with which programs are delivered, because you're doing a better job of targeting them on the people with the high value added. This is related to the problem of graduate admissions that we were discussing before the lecture today. All right, so the usual parameter of interest is the average effective treatment on the treated. This parameter is useful because it's an input into a cost-benefit analysis that addresses the question, should we keep the program as it is or get rid of it entirely? Right? So if you know the average effect of the program on all outcomes that you care about, if you convert those average effects all into current dollars, right? There's a whole literature on cost-benefit analysis that talks about how to convert non-monetary outcomes into monetary terms. Then you can compare that average monetary impact or monetized impact to the average cost of the program and do a very simple social cost-benefit analysis and say, keep it or dump it. Was there a question or just a yawn in the back? Just a yawn, okay. In an experiment, right, so E of y1 minus y0 given D is equal to 1, y1 minus y0 is the treatment effect, the difference between the two counterfactual, the two outcomes, one of which is counterfactual. For the treated units, that's the conditioning on the D equals 1. You can break that up into two parts. The expected treated outcome for the treated units, that's easy, right? We just measure that using the observed treated outcomes for the treated units. That's not the hard part. The hard part is the second term, E of y0 given D is equal to 1. That's the economic outcome, or the whatever outcome, that the treated units would have experienced had they not been treated. In an experiment, we get that in a very simple way. We force D equals 1 units. D equals 1 units are units that wanted to be in the treatment and would have been in the absence of the randomization. We force D equals 1 units to experience the untreated outcome at random. That's that second term in the bottom equation. E of y0 given D equals 1 and R equals 0. Those people are forced to experience the untreated outcome. Essentially, they get to provide the public good of knowledge about what would have happened to the participants had they not participated. And there's a little literature that argues about the ethics of not compensating those people, which typically they are not compensated. That's a good overview topic in there. Okay, any questions at this point before I launch into this simple model? All right, so this model is useful to help organize our thinking. That's a phrase from Costas Magiri that I've always liked. Organize our thinking with the model. This model can be found in Heckman and Robb, 1985. If you have not read Heckman and Robb, 1985, which I always mentally called the Old Testament when I was a graduate student, not read the Old Testament, it repays reading. Much of what happens afterwards in the treatment effects literature is anticipated in Heckman and Robb. It is very long. There's a journal version and there's a book chapter version. They're both pretty long. Someone once described this as a core dump of everything that was in Heckman's head in 1984. For those of you who don't know what core dump means, which may be everyone but Larry, back in the days of mainframe computers, if something went wrong, the entire contents of the memory of the computer were written out. And that memory was called the core. And so that writing of the contents of the computer's memory out was called a core dump. So Heckman and Rob 85 is a Heckman core dump from the early 80s. The model also appears, somewhat revised, in the Heckman, Lalonde, and Smith Handbook of Labor Economics chapter from 1999. And it appears again, updated and revised, and with additional theoretical material about the dynamics of the problem, which are not present in this simple model, in my recent handbook chapter with Brian McCall, who's a colleague of mine at Michigan, and Connie Wunsch, who is at Basel. So, in this model, oh, there it is. In this model, we have this outcome equation here. So why is this outcome that we care about? We have individual units I. Those can be people, like in a job training program. They can be countries, like in a study of the treatment effect of democracy. We have T, which is the time subscript. We have some conditioning variables. Those can be there to soak up residual variance. Those can be there to solve, in part or in whole, a problem of non-random selection as treatment. We have a composite error term that has two components. One component has no time subscript. So this is a unit-specific time invariant outcome component or fixed effect. That's the eta I. And then there's this time varying error component. It's useful to distinguish these two because A, they help us to think about the nature of the selection problem. Right? It could be that units select into treatment based on the time invariant unobserved component of their outcomes. Or it could be that units select into treatment based on the time variant unobserved component of their outcomes, or both. And the empirical strategies that you would use, the identification strategies that you would use, depend on which of those two things is important, or both are important. And then there's this bit here, which is the treatment effect. So DIT is an indicator variable for whether you have been treated in period T. Beta DI is the unit-specific effective treatment for unit I. Now note, this seems at some level a bit complex, but in fact there's already a huge amount of simplification here. Right? So I have assumed that everything enters this model in an additively separable way. Be true. So there's no complicated interactions or anything among the x's. There's no interactions between the d and the x. Blah, blah, blah. Right? So this is a general model, but it's not as general as it possibly could be. The observed outcome YIT is just whether you're treated or not in period T by period T. So the way I'm thinking about this is once you get treated, you stay treated. And having been treated affects your outcome in every subsequent period. Note, too, that there's no variation of the treatment effect in relative time in this setup, which might be important. Right? It could be that the treatment effect is big right away, but then it fades out. Right? You forget what you learned or whatever. It could be that the treatment effect is small right away, but it gets bigger. That is going to be context dependent. For simplicity here, there's no absolute time or relative time subscript on the estimated treatment effect. The treatment effect could also vary with calendar time, right? Maybe it depends on the business cycle, for example. I'm going to assume in this model that the treated outcome in period K is 0. So the inspiration here is the job training context. We imagine that there's time is running along, there's one period K in which a job training program or a treatment becomes available. And you have to make a decision in that period K, am I going to participate or not? If I participate, then in period K, I get 0 for Y, because I'm busy getting training. That's the notion. And then in every subsequent period, I get beta DI. So it's an investment, like in the standard Becker-Mincer model of human capital. I pay a cost now, which is getting a 0 outcome in this period K, and I get something back, hopefully, if beta is positive. I get beta DI in all future periods. So this way of setting up the problem, where the treatment appears only in period K, abstracts from the question of dynamic participation in treatment. So this is what we talk about in McCall, Smith, and Wunsch. We lay out this model, and then we say, okay, let's think about models of treatment being available in every period. And my thinking about, say I'm an unemployed person. I'm an unemployed person in Germany. Right? So in Germany, everything is very organisiert. You register as unemployed, and they keep track of you, and there's a caseworker, and you have to go out and meet with the caseworker pretty regularly, and the caseworker has astounding amounts of power over you relative to the US case, where we don't trust the caseworkers as much. And, and you may be unemployed for a much longer time in a lot of European contexts than typically would be the case in the US. And so you may be thinking, okay, how long should I wait? And the caseworker may be thinking, how long do I want to let this person search with their current skill set before I make them take training and get a new skill set? Right? That is not addressed in this version of the model, because the training only appears in this one period K. It is addressed in other models that have come into the literature sense that we talk about in the new handbook chapter. So we're abstracting away from that for simplicity. It's just one shot, period K. I've said all the rest of that stuff. The second part of this model is a participation equation. It's a model that determines who chooses in period K whether to get the treatment or not. So that model has three important features. All right, so we have a standard latent index set up here. So DI star is a continuous latent variable that you can think of as the net utility from taking the treatment. So this is going back to something Larry was mentioning before we started this whole class of going back to the Mansky and McFadden kind of choice models, where you integrate these discrete choice econometric frameworks into a theoretical choice framework. That's where this kind of thing comes from. All right, so there's a latent index, D star, that is a net utility of participating. That depends on four things. It depends on the direct costs of participation C. Right, so in a schooling context, that's like tuition. It depends on the opportunity cost of participating. So in this simple model, right, what you give up to participate is you give up Y0K, because you get 0 as your outcome in the period to participate in period K. So the opportunity cost here is Y0K. The third thing is the treatment effect, right, beta DI. And as I note down here, this formulation assumes that agents know their treatment effect. Right? The way I've written it down here, there's no beta DI hat or E of beta DI or anything else. I've assumed they actually know beta DI. There is a whole, as I say down at the bottom, there's an empty field, basically, waiting for you to come and write papers about the extent to which agents know their treatment effect in any context. I can point you to a couple of papers, but basically this is wildly understood. And it's pretty important. Right? If agents have no idea what their treatment effect is, so they are making decisions, if it's basically random noise, that's very helpful for evaluation, right? Because it's making the selection problem less severe. If part of, right, suppose that beta DI, the beliefs about beta DI are completely random, unrelated to everything else in the world. And suppose that people believe, in fact, that they really know beta DI, and so they assign a high weight to it in making their decisions. So that's great. That's like random assignment, right? It's kind of bad from an efficiency standpoint, because if people think they know their beta DI and they don't, then they're not choosing in an efficient way to participate. Or if you have a program with a gatekeeper, like a caseworker, and they think they know everybody's beta DI, but they don't really, then they're not allocating the treatment efficiently. But from the evaluator standpoint, this is great if people are participating at random, right? It's much easier to credibly argue that you've solved the selection problem. But this is something that, in general, we just don't know. There's one study in the US that's in a special issue of Labor Economics that I edited that engages with something called the AFDC Homemaker Home Health Aid Experiment. So this was a program, AFDC used to be the welfare program for single moms in the US. And this was a treatment that attempted to train women who were receiving welfare to be home health aides or homemaker aides. So they would go into people's houses and help them with minor health issues and with dealing with homemaking things that they weren't up to because of the state of their health. In this study, which was an experimental study, they asked the caseworkers, before anybody was randomly assigned to treatment, for each person they asked them, basically, what do you think this person's Y0 is going to be, and what do you think their Y1 is going to be? Well, actually, they asked them their Y0 and their Y1 minus Y0. So they asked the caseworkers to predict the untreated outcome. They asked them to predict the treatment effect. If you interact the caseworker predictions with the treatment indicator in your experimental impact regression, the coefficient on the caseworker predictions of the treatment effect is 0. Right? So in that particular experiment, which is basically the only evidence that we have about caseworker knowledge of treatment effects, in that particular experiment, they knew nothing. That's kind of a bummer, right? That seems like something we ought to worry about on several dimensions. There is another paper that I have with Michael Lechner, which is a selection unobserved variables-based non-experimental paper using Swiss data, very rich Swiss data, where we look at caseworker assignments of individuals to different activities within the Swiss active labor market program. And we predict for each person their outcome associated with each of the 9 different treatments in Swiss active labor market programs. And then we look at the caseworker assignment, and we compare the average outcomes associated with the observed caseworker assignment to the average outcomes if you assigned everybody to the treatment that would give them the best outcome. Now, as we note, there's general equilibrium issues here. So we do this with and without capacity constraints, with and without forcing the number of people assigned to each treatment to be the same as it is in real life. What we find is that the caseworkers do about as good as random assignment. They could do better, they could do worse. That's another indication that caseworkers don't actually know, in some sense, one important aspect of their job, which is the assignment of individuals to treatment. That they don't know what beta DI is, and so they are not exploiting all of the gains to society that they could get from spending the money. Johannes.
But isn't this problem even more severe if you have treatments that last for several periods, because then the dropout rates become endogenous to that, no?
Yes, yeah.
So in that sense here it's probably not so severe because it's just a one-shot intervention, no?
Yes, although I haven't told you how long the period is, but
okay,
yes.
That's important.
No, I think this is wildly understudied, and you know there's a point you reach in your career where you have a long list of ideas in your head of papers that you want to write, and you observe that there is a cap T at some point to your career. Hopefully that's 20 years away or something for me, but still it's there, and I think about it. I think, okay, I've got 20 years left. What am I going to write? The list of topics in my head would take more than 20 years to do. And so now I just throw paper ideas out and hope somebody else writes them. Because then I can cross them off my list and be happy if they did a good job. So this is not just a paper idea. This is like a whole area that I think is very understudied. Jim has a paper with I hate to say this because with a student, right? Because this always happens to me. Not so much anymore, but when you're younger, it's Heckman and you're the and. And anyway, Heckman has papers with students that try to do a bit of this also in the context of going to university or not. If we think about heterogeneous treatment effects at university and people selecting in university, how much of their treatment effect from university do people know at CNT? And he comes up with a number that's 0.3 or something. So there's a little bit of literature, but there's not much. Lots to do there. Yes?
Just a clarification. This equation could be also defined as a first stage in a two-stage equation, or is something completely different?
No, this in the classic bivariate normal selection model, right? This is the selection equation.
Okay.
Now, the classic bivariate normal selection model, right? If you look at the model in Heckman 79, that kind of related literature, the treatment effect isn't in there. Homogeneous treatment effects are assumed. If we have homogeneous treatment effects, then this term gets soaked up into the intercept, right? Because it's the same for everybody. In the Bjorklund and Moffat paper, so I don't know, have you heard of the Bjorklund and Moffat paper? You have seen They have this paper that's in the Review of Economics and Statistics in 1987, something like that, that is a heterogeneous treatment effect version of the normal model. So it's a trivariate normal selection model, where you can have selection on both y0 and on y1 minus y0. And so they just add normally distributed treatment effects to the normal model. And that paper sort of anticipates the whole later literature on marginal treatment effects. But it's wildly understudied, it's wildly underread and undercited, because in some sense it was too early. People didn't really, it reached out to Fine Journal. I'm happy publishing's there, but this paper, which should have placed in the top 5 ex post, given its importance, did not place in the top 5, placed in Restat. It is cited, it's got some cites, but given its kind of role in anticipating this whole later literature, it is astounding how little impact it had when it first was published. People didn't really start citing that paper until Jim started doing the marginal treatment effect stuff a decade later. And then people said, oh yeah, look at this earlier paper, it sort of anticipates. And it's not like Moffat is somebody nobody's heard of, right? And it's kind of, Bjorklund actually is a big guy in Sweden. Done a lot of stuff on inequality. So yes, if you want to think about the bivariate normal model, right, then you write down an outcome equation and you assume that epsilon has, you probably cross out the a to I, probably you just have cross-section data, but maybe you don't. There's longitudinal versions of the normal model. And you assume that these errors are normally distributed, and then you have your participation equation, and you assume that this part, which is the 4th part, the unobserved part of the latent utility from participating, is also normally distributed. If it is 1984, then you just plow ahead, right? You impose the functional form assumption. You don't worry about whether there's different variables in here than there were in here. You don't worry about whether you have an exclusion restriction. You just impose the functional form, produce estimates, and say, aha, I solved the selection problem, right? Now, over time, people came to realize that the standard bivariate normal model didn't behave very well unless you had different variables in the participation equation than you had in the outcome equation. But that took a while for people to figure out. So there's a paper by Art Goldberger, who was at Wisconsin for his, I think, whole career, famous econometrician. It has one of my favorite paper titles. It's called Abnormal Selection Bias. And it's one of the papers that makes the case that the normality assumption it needs to be supplemented with some actual data, some actual variation, an exclusion restriction, a variable that affects whether or not you participate, but doesn't affect outcomes other than through its effect on participation. So that, in turn, right, kind of anticipates the instrumental variable literature, which says, well, if you've got that, if you've got an instrument, then why bother with the normality assumption, right? And then you get into the whole late literature and blah, 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 right? So what you can see here, right, a lot of instruments in program evaluation contexts are based on C, on cost. So think about the classic David Card paper using distance to college, right? That's an example of a cost-based instrument. The idea is that distance to college is part of the direct cost of going to college, but arguably, and of course people do argue about this, arguably distance to college should not appear in the outcome equation. The only way it affects outcomes is by affecting the choice of D. Right? You can embed that in the normal model, or you can just do instrumental variables, right? In which case you estimate this equation with a linear probability model, right? And then you put D star, you put D hat, I should say. Right? You estimate this equation with D as the dependent variable, and then you put D hat into the outcome equation. And that's two-stage least squares, the IV version of this. Is that kind of, that's probably more than you were looking for. So, you're right to see the link with the standard bivariate normal setup here. Let's see, what else do I want to say? Blah, 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 blah. Yeah. Okay. So, suppose that the beta I are independent of everything else in the simple model, and suppose that individuals know them, and select upon them, then what can we say about the ordering of the standard treatment effect parameters? So I define the average treatment effect on the treated. Its mirror image is the average treatment effect on the non-treated, right? The average difference between Y1 and Y0 among individuals who are not treated. And then the average treatment effect in the population is the weighted average of the ATET and the ATNT. Can I say anything about the ordering of those in this model if the beta I are independent of everything and people know it and use it to select into the program? So here's the place where the fact that I only know two people's names comes into play. So Sasha, what is the answer to that question? See, you should have been aware, because you knew that you were one of the two people whose names I knew. So, in the simple model, right, suppose that the beta DIs, and there should be a D subscript there, suppose the beta DIs are completely independent of everything in the model. There's treatment effect heterogeneity, but it's related to nothing. It's just random. Nature has randomly assigned you a treatment effect. And individuals know their treatment effect, and as in this equation, the treatment effect is part of the choice. In that world that I just described, can I say anything about the relative magnitudes of the average treatment effect on the treated, the average treatment effect on the non-treated, and the average treatment effect on the population? And I don't know a defined response. I'm happy with that. Anybody else? Yeah, I didn't expect it to call. Johannes?
Well, if it's really complete, so random meaning in the sense that participants wouldn't know ex ante.
No, participants know their treatment effect, but it's unrelated to everything else in the world. You're just nature has randomly assigned you a beta DI, and you know it. And because you know it, it affects your decision to participate or not. But it's not correlated with C, it's not correlated with Y0, it's not correlated with U.
No, I mean, then I would think you wouldn't know. You couldn't tell the differences.
So I would argue, in fact, that in this world, the average treatment effect on the treated is going to be larger than the average treatment effect in the population, which is going to be larger than the average treatment effect in the
Because
non-treated.
so the treated selected in knowing the treatment
Exactly.
effects. Okay.
Exactly, right? That's what this model says, is that the treatment effect is in here.
Okay.
Presumably it has a positive coefficient, right? That you're more likely, your latent utility from being in the treatment depends positively on the treatment effect. Now, for some treatments that might not be true, right? If this is a treatment to get people to stop smoking marijuana, then people who really like marijuana might not want to have a big treatment effect in the program. But for most programs, for labor market programs, you're going to want to have a bigger treatment effect, right? So if people know their beta DI, and this coefficient is positive, and if beta DI is unrelated to everything else in the model, then that's going to induce selection into the program based on the treatment effect, right? So the average effect of treatment on the treated is going to be the average treatment effect on people who differentially had good treatment effects. Because conditional on everything else, they're going to be more likely to participate in the program. Similarly, the non-participants are differentially going to have bad treatment effects. Right? They may still be positive, but they're smaller. And so they get outweighed for many of those people by other factors, by the direct costs or the opportunity cost. So in that world, we would expect a very clear pattern here. We would expect that the treated units, on average, have a bigger treatment effect than the untreated units. Now, what's the implication of that? If we think about not the cost-benefit analysis that's associated with keep the program as it is or get rid of it, but we think about a policy change where we increase the number of people who are brought into the program. Right? So let's say that we add a little subsidy to being in the program. Say, okay, you be in the program, we'll give you $10 a month as a stipend. Right? So what we're going to do in this model, if we do that policy, is, we're going to bring in some folks at the margin, right? Without the subsidy, it wasn't worth it to them. With the $10 a month subsidy, now their D star climbs above the threshold. But those marginal people, their treatment effects are going to be smaller than the average of the people who are already treated. Right? Because they're people you have to drag in at the margin. If they had really great treatment effects, they'd already be there. Right? So the way I think about this as an example is there's a book by a famous demographer called Linda Waite and a journalist co-author called The Case for Marriage. And because I'm a geeky guy, I read this book when I was deciding whether or not to get married. And I read some other marriage books. I thought I should do big life decisions, right? I thought I should do my research and figure out what my treatment effect was likely to be. I was 40 when I got married, so I waited a long time, partly because I had the view that my treatment effect might not be very big. And so I read this book, and the book, it's a very nice book. Each chapter is a survey of the literature of the effect of marriage on one particular class of outcomes. So there's a chapter on labor market outcomes, there's a chapter on health outcomes, there's a chapter on sort of good behavior. It turns out that there's a very clear treatment effect of marriage on how many fights that men get into. Married men fight a lot less than unmarried men. And the authors thought this was a very good thing. And it's interesting because these different literatures come from different disciplines, so they have very different styles. So you learn something about styles of empirical work from reading this book. And then the final chapter is policy recommendations, right? And this is where you always go wrong with sociology books, right? You get to the last chapter with the policy recommendations. And I'm a big lover and consumer of sociology, but I always have trepidation because I'll really be liking a book. But I know that chapter is coming at the end of the policy recommendations, right? And I know they're probably going to get it all wrong. Anyway, in this book, they assume throughout implicitly that marriage has a common effect. And so, of course, after they've shown you chapter after chapter where the effect of treatment on the treated is positive, they get to the end and say, well, everybody should be married because of all these positive treatment effects, because they're thinking they're in a common effect world. But if you think you're in this world here, right, where in fact there are heterogeneous treatment effects of marriage, and people have some idea of what their treatment effect of marriage is, so that what we currently observe is a world where people who thought their treatment effect of marriage is going to be positive tend to get married, people who think it's going to be negative tend to not get married, then the people all these policies are going to bring into marriage are not going to have as their treatment effects the treatment effects on the treated that they are discussing in these chapters. And so because they haven't thought about it in terms of heterogeneous treatment effects, and because they haven't thought about a simple model of selection into marriage, the policy recommendations at the end of the book are completely foolish, right? And could in fact make things much worse off. If they really induced a lot of people into marriages whose treatment effects of marriage were negative, that's not good for society, right? It's not good for those people. So this stuff matters, actually, for policy. It matters both for our understanding of the world, and it matters for getting the policy right, to think about heterogeneous treatment effects. So this is part of the lecture that is ranting at you to try to get you to take heterogeneity of treatment effects seriously, both in your own work and just when you read the newspaper or discuss policy. Right? It actually affects how you think about what we should do.
So did you get it right, the treatment effect? Was it positive?
Yes. but I think I would say too, and this is not, my wife is wonderful. But it's also true that my Y0 was very high, that I really enjoyed being single. And I had that right too, right? And so, yeah, but it was good to read the book because it's a good example. So been married 14 years, hard to believe. Okay, any other questions about that? I'm going to talk a little bit about implications of this model for, I'm going super slowly today, but that's all right. It's all good. I'm going to talk about implications of the simple model for the implied econometrics of this problem. And then we're going to jump into the heterogeneous treatment effects part of more generally, but maybe we have to take a break at some point. Any more questions at this point? All right, so let's think about the simple model in terms of, all right, this is how we're thinking about the world. We have some data on some treatment, and we want to estimate a treatment effect. An average treatment effect on the treated probably is what we're looking for. How does the model help us with that problem? Right, so this is another one of the themes that I intend to have in this lecture, which is these things all go together. The institutions, the theory, the applied econometrics, things are strongest, things are most compelling when those are all brought together. This is part of why I wanted to work with Heckman. So I originally started working with Becker because Heckman was at Yale from 1989 to 1991. They were trying to recruit him. And everyone in Chicago thought he was gone. Right? You know, it's the posh East Coast University, and he bought this great house that he always talks about. He still misses this fantastic house he had in New Haven that would belong to Oliver Williamson, blah, blah, blah. But in the end, he came back to Chicago. And he would tell you it's because the students were rubbish at Yale. Anyway, he came back to Chicago, but it wasn't clear he would. So I started working on a dissertation with Gary Becker, brilliant man, wonderful. But I was a much better match with Heckman. And part of why I was a better match with Heckman was I really liked the feature of his empirical work, that there was always this integration of the theory, the institutions, and the applied econometrics. So I'm trying to sell that to you as a way to do work. All right, so suppose that we want to do a selection of unobserved variables kind of strategy. So exogeneity, right? This is the way that we would write exogeneity in an undergraduate textbook. We can also think about conditional dependence. What's the difference between conditional dependence and exogeneity? Conditional dependence just gives you a causal interpretation of the coefficient on the treatment effect variable. It says, I don't care about those coefficients on the x variables. The x variables are just there to help me with conditional dependence, to help me with this claim that I have solved the problem of non-random selection into treatment by conditioning. We will talk a bit more about that. Some people think that's never true. Some people think that's always true. I think it's occasionally true. So here, this just says, remember, we have a composite error term, right? It's got the part with the I subscript and no T subscript, and the part with both. That's the whole error term. I could call that U or eta or something. That expectation is 0. Conditional dependence just requires that once I condition on the x, knowing the value of d doesn't tell me anything about the value of the error term. So I'm going to assume conditional dependence here. What do we need to condition on to make that true? Well, we need to condition on stuff that is going to proxy for eta I and epsilon it. Right? Well, eta I, what can we condition on that would proxy for eta I? Well, that's actually pretty clear, right? Because eta I is in the outcome in every period. And so if we condition on lagged outcomes, so yi k minus 1, yi k minus 2, yi k minus 3, we condition on enough outcomes, and how many is enough depends on the relative variance of eta I and epsilon I. If eta I is most of the story, then I only have to condition on a couple of lagged outcomes to mostly solve the selection problem. If epsilon I is also important, then the lagged outcomes have a lot of noise relative to eta I, and so I need to condition on more of them. Right? So in the Heckman, Lalonde, and Smith handbook chapter, we have this nice section where we do a set of simulations, basically using this model, but without many covariates, where we vary characteristics of the data generating process, such as the relative variance of eta I and epsilon I, and we show how that affects the performance of different standard applied econometric evaluation estimators, like difference in differences, like conditioning on lagged outcomes, and so on and so forth. One nice thing about that handbook chapter, which is also true of the handbook chapter I wrote with Brian and Connie, is that you don't have to read the whole mighty opus. right? So the Heckman, Lund, and Smith is almost 200 pages. But there are sections of it that you can read as standalone, almost papers. And indeed, we talked about turning the simulation part into a paper. Never did. That makes it less intimidating. I think you don't have to read the whole 200 pages. So I encourage you to just go read the simulation part, because I think it provides a lot of intuition. So the model, right, tells us something about how we can get to conditional dependence, how we can make a case for conditional dependence. If there is non-random selection on A to I, I'll come back to that in a second, we can partly, and how partly depends on how many periods we have, and on the DGP, as I mentioned, we can partly get to this place, this conditioning place, by using lagged outcomes as a proxy for A to I. That's the model, right? This is what is commonly done in the literature on active labor market programs, is precisely the condition on lagged outcomes. We probably don't think that those coefficients on lagged outcomes are causal, so we probably want to be in a world where we're assuming conditional independence, but we think they're helping us condition on the A to I. Now, another feature of this model is selection on untreated outcome levels. So the answer to the first part of that question is yes, there is selection on untreated outcome levels. What's the nature of it? How does it work in the model? And what's it going to look like if we graph the average earnings of participants? So this is a question number 2 here, about selection on Y0, on the untreated outcome. Where does that come into the model? I'm not going to tell you. It comes in through here, right? So the opportunity cost is in the latent index for the value of participation, right? The bigger is Y0K, we would assume that this gamma Y has a negative coefficient, right? That the better the labor market opportunity in period K, when the training is available, the less likely I am to participate, because the higher the opportunity cost is for me. Yes?
But so how long is this intervention here?
Well, let's think about K as like a quarter, like 3 months.
Okay.
Let's say. In Germany, sometimes they will send people to training for a year or 2.
Yeah,
In
that's
the
what I was
US, it's
asking.
usually more like 3 months. But they also have the Kurz training in Germany, which is the short training, which is more like the 3-month kind of thing. And one of the features of the German system is that they're sort of fads, right? They go through this cycle of one period they like long training programs, the next period they like short training programs, and they go back to long training programs. Yes?
But the 2 questions that you had put before cannot be related. Maybe can be related to a problem of imperfect compliance into treatment, or is.
Tell me more what you mean by imperfect compliance.
Maybe you assign to someone to be in the control group, but they know the benefit of participating, and they just, they try to get the treatment. And
that you could modify this model into a model of imperfect compliance. Yes. So here I've been thinking about experiments as not having compliance issues, but they often do have compliance issues in practice. But if people were not going to comply, the people in the control group who should try not to comply are people who think their opportunity costs are low and their treatment effects are high. Right? So the selection on untreated outcomes works through Y0IK being in here. Right? And because of the fact, if we assume that the epsilon ITs are serially correlated, which I think is a reasonable empirical assumption, then selection on Y0IK implies both non-random selection to treatment based on A to I, based on the time invariant component of outcomes, and non-random selection to treatment based on epsilon IK, right, the transitory component of outcomes. And if we assume that the epsilon ITs are serially correlated, then the selection on the transitory shock will extend into periods prior to participation because of the serial correlation. Right? So if you think about a possible transitory shock of being job loss, right, then you might lose a job 2 quarters before you decide to go into training, but the job loss persists for the 2 quarters, and so you get both persistent selection on the time varying component of the eta I, and you get this selection of transitory shock that is increasing as you get closer to the date of selecting the training program. Right? So if you think about the serial correlation as having a coefficient of 0.5 or 0.6 from epsilon ITs, then selection on the transitory component is going to be less and less important as you go back over time. Pretty happy with that. Right? So I mean, you look at this model, and it's not trivial, but it's also not super complex. And yet, it incorporates very rich behavior. This is one of the things about theory. Right? I'm not a big deal theorist at all, but even relatively simple models can have incredibly rich implications and be super valuable for organizing how we think about problems. So here's some data. Right? I think one of my favorite stories from graduate school about a guy called Sherwin Rosen. When I was in Chicago, famous guy, kind of a bit of a crusty guy, kind of grumpy a lot of the time. It was never clear to me why. I thought, here's this guy who's really successful, right? He has a job at one of the top departments. He's written a lot of wonderful papers that I wish I could have written. And yet he always seemed unhappy to me. Anyway, that's a mystery. He had a negative happiness fixed effect or something. Anyway, we were sitting in a seminar, and the seminar was a paper that had a model in it, and then it had some empirical work. This was a style of paper actually that's gone out of fashion, where you would have kind of a little applied theory model, and then you would test comparative static predictions from the applied theory model by running some regressions, basically. And the person had spent most of the seminar on their applied theory model, and Sherwin was getting tired of hearing about the applied theory model, so finally he said, "Let's look at the goddamn data." And so we moved on and looked at the goddamn data. But I have been in many seminars since then where I've had exactly the same thought. It's like, you don't really know the model, let's just look at the goddamn data. Anyway, so here's some data. So this is from an experiment that we're going to say a little bit about later in the second talk, called the National Job Training Partnership Act study in the US. So this is the experiment that generated the data that both Pepper and I used for our dissertation research. And what I'm showing you here is male adults and female adults. This is from Heckman and Smith, 1999, in the Economic Journal. Month T here is month K in the model. So month T here is the month of random assignment for people in the experiment, and it's a month of measured eligibility for people in the non-experimental comparison group. Okay? So this experiment featured parallel data collection on an ideal non-experimental comparison group that was located in the same local labor markets as the people randomly assigned. And so I only want you to pay attention to 2 of the lines here. So this line up here for the male adults is the eligible non-participants, so the non-experimental comparison group. These are people who are all eligible for the program in month T, but chose not to participate. This line here is the experimental control group, not treatment group, experimental control group. This feature here, where the mean earnings of this group, so these are months, so we're going back a year and a half, so the mean earnings at the monthly level of the control group are falling in the months leading up to the period of random assignment. That phenomenon is called Ashenfelter's dip. So it was first identified in Orley Ashenfelter's 1978 Restat paper on a program called the Manpower Demonstration and Training Act. That was a program in the 60s in the US that was designed to retrain workers whose jobs were going to be taken by robots. I'm not making this up. Right? So there was a big panic in the early 1960s, just like we're having a big panic now in the US about all the jobs being taken by robots. Now, last time the jobs weren't all taken by robots. Maybe this time they will all be taken by robots. But it is not a new concern. So Ashenfelter's dip, what does this mean, right? Well, what you see is what I was kind of setting up when I was talking about correlated epsilons plus selection on eta. So There's a kind of fixed difference for the first 6 months here that looks like selection on eta. It looks like the eligible non-participants, on average, had higher earnings in a persistent sense than the people who were ultimately going to try to participate in the program in the comparison, in the control group, I should say. Right? You see that over here too. But it also looks like there's selection on the transitory shock. Right? That's the dip. Right? No individual person actually experiences a gentle decline in earnings. That's an aggregate phenomenon. What individual people experience, is they experience their earnings falling to zero. Right? So they experience job loss. Some people lose a job at K-5, some people lose a job at K-2. And what's true among the participants is that differentially people lose their job here rather than here. And so if you have this pattern of everybody looks like this, but more people lose their job close to the month of participation, you get on aggregate this gentle dip in the mean. So this is an ecological fallacy example, if you will, to borrow a term that economists don't often use, but is a very useful term, where the aggregate pattern doesn't look like the individual patterns. Right? The aggregate pattern is the ecological pattern, if you will. Right? So this graph here is perfectly consistent with the model if we assume serially correlated epsilons, because it illustrates both selection on eta, on the time invariant unobserved component, and selection on epsilon, selection on negative labor market shocks. Johannes, on a Praga.
Just to clarify this, I mean, okay, once you assume very serially correlated epsilons, they are no longer really transitory, no? I mean, they become
Well, in
sort
a
of like a
limit,
permanent shock.
if epsilon goes, 0.999, then it's become pretty close to eta.
Yeah,
right?
exactly. So how serially correlated do you need them to be to justify this pattern?
Well, let's go back a sec. So this model, the thing that, it's a model, it's not truth. Right? So an abstraction that has been made is we have abstracted away from employment. Right? So if you think about, earnings have a big mass point at zero among the sorts of people who participate in these programs in the US, right? And that reflects employment. And this model doesn't really capture that. If we think, especially if we think about epsilon as being normally distributed, we're not going to get a big mass point at zero, and we're going to get a bunch of negative earnings values that we shouldn't have.
Yeah.
You can do a more complicated version of this model in which you have kind of a two-part process, right? There's an employment process and an earnings process that's conditional on employment. That would be a more realistic model. Because as I said, what's really happening underneath Ashenfelder's dip is not that people are experiencing gentle dips in earnings. There's actually a little of that. People, overtime goes away before the firm closes, that kind of stuff. But mostly people are experiencing that.
Okay.
And that's not well captured in this equation, right? Because where the persistence, there's persistence both in being stuck at the zero mass point because of job loss, and there's persistence in I just happen to get a really good job that pays me more than my marginal product. There may be persistence in that was not a good example. There's persistence in demand shocks at firms, right? So if you think about overtime, for example, as a reason, as an epsilon, that may last longer than one period, right? So my firm experiences a positive demand shock, so I work a bunch of extra hours for 6 months. That looks like serially correlated epsilon.
Okay.
Okay?
That's right.
So it's always good to think about the periodicity of the behavior relative to the periodicity of the data, right? If the data are annual, and demand shocks are all annual, then we don't have to worry about serial correlation. If the data are monthly and the demand shocks are annual, then we do need to worry about serial correlation, right? So part of your prior or your worry about how big does the serial correlation in epsilon need to be depends on the relative periodicity of the shocks versus the data, right? So you think about macro, right? If we have annual data, well, business cycles don't happen on an annual level. Business cycles happen on kind of 7-8 year kind of deal, right? And so you worry about serial correlation with annual data, or even more with monthly data. That kind of. that answer your question?
Yep.
Okay. So this is a very powerful model. Not a perfect model because it ignores employment, which affects, a lot of these shocks are really people being put down to zero if we're thinking about earnings as the outcome variable. But it captures a lot of behavior, and it even captures this pretty complex selection here, where we have very clear evidence of selection on both the transitory component of outcomes and the permanent unobserved component of outcomes. Now you'll note for the adult women down here that there's much less evidence in the raw means of selection on the time invariant component of outcomes, but still evidence of selection on the transitory shocks. That's interesting. I don't know why that would be. Why would there be more selection on the time invariant component for men than there is for women? Don't know. That's actually understudied too. People always do these evaluations separately for men and women, but there's very little thought about why. Right? We know there's often different treatment effects for men and women in active labor market programs. We know there's often different participation behavior for men and women, but there's very little attention to the sources of those differences between the two groups, which there's another paper. All right, I want to go on and discuss now, change gears a little bit. I'm going to proceed with the first set of lecture notes for a while. We'll see how much time is left for the second set of lecture notes, but you have them. But there's some more material in these lecture notes that I want to cover. So now I want to think about what we get from an experiment or from a successful non-experimental identification strategy. What we get from an experiment is two marginal distributions. Right? We get the marginal distribution of the treated outcome, that, and we get the marginal distribution of the untreated outcome. That's sufficient to do a lot of things. The marginal outcome distributions are all you need to estimate the average treatment effect. They're all you need to estimate marginal treatment effect, if you go down that road. They're all you need to estimate quantile treatment effects, which we're going to discuss shortly. But they are not all you need to estimate everything you might be interested in, or I should be clearer, to identify everything that you might be interested in. So there are parameters that we might care about that require the joint distribution of y1 and y0. What does the joint distribution provide that the marginal distributions do not provide? It provides the link between where you are in the treated outcome distribution and where you are in the untreated outcome distribution. Right? We can think about a world where people who do well in the treated outcome also do well in the untreated outcome, and vice versa. We can think about a world where the treatment is transformational in some sense, so that the mighty are brought low and the lowly are raised to the peak of the mountain, or whatever. There's some biblical phrase that I'm searching for and not getting the nice prose from the King James Version, but that's the idea, right? That's a world where y1 and y0 are negatively correlated. Those are very different worlds, and as I'm going to show you, those have very different implications for the distribution of treatment effects, right? For the distribution of y1 and y0, which of those two worlds we're in. So some examples of parameters that we might care about that depend on the joint distribution of y1 and y0 are the fractions you gain or lose from the program, the percentiles of the distribution of impacts, so the distributions of beta di. Right? What does that look like? The impact variance. It's just a feature of the distribution of beta di. The outcome correlation that we just talked about. Those are all really interesting objects that we don't talk about very much. And the reason we don't talk about them very much is that they depend on something that is very hard to get, namely the joint distribution of y1 and y0. So what I want to talk about now is ways that people have sort of thought about trying to pin down that joint distribution, or more generally, extract meaningful treatment effect heterogeneity from the data. So this bit draws originally on my job market paper, which was Heckman, Smith, and Clemens, 1997. Clemens was a PhD student in statistics at Chicago who I met in Stephen Stigler's class on robust estimation, and then lured into working for Jen, which I'm not. Her treatment effect was not super positive, but I think she learned a lot. This paper I mentioned before that I did with my student Eva Jabari is partly Heckman, Simpson, and Clements updated and rewritten. It reflects developments in the literature on this topic in between 1997 and 2008. It's one of my favorite papers of my own. If you want to look at a recent paper that goes down this road to some degree, that also, which is something we do not do in Heckman, Smith, and Clements, and Jabari and Smith, something that really explicitly incorporates an economic model into its reasoning. So it uses an economic model to place restrictions on the joint distribution of Y1 and Y0, and it sees how much mileage you can get out of those restrictions. This paper by Pat Klein and Melissa Tatari in the American Economic Review is very nice. A very nice paper, a paper I wish I had written. All right, so let's start with a very simple example, which is why I wanted to have this whiteboard today. I'm trying to make it, move it away from the speaker. So the shuttle tonight is at 7 p.m. and the shuttle tomorrow is at 9 a.m. And I'm going to erase that information, important though it is. And I want to think about a binary outcome, binary treatment context. So let's call our binary outcome employment. Let's say employment in the 18th month after random assignment in an experiment. So I'm going to talk about all this stuff in the context of an experiment, just so we don't have to deal with the selection problem, but it all generalizes to a non-experimental context. Let's see, rows are controlled. So NE is not employed, E is employed. The columns correspond to the treated state. The rows correspond to the untreated state. The data from the experiment give us the marginal distributions. So, as it says up there, in the control state, 60% of people are employed, 40% of people are not employed. In the treated state, 20% are not employed, 80% are employed. So this is a wildly and unrealistically effective program, right? Because it increases the probability of employment by 0.2. There aren't any real programs that do that. So what we're seeking, right, is the joint distribution of outcomes. That's the 4 cells in the table, right? We have a binary outcome and a binary treatment. The joint distribution is defined by those 4 cells. The problem is that there are 3 unknowns, right? So the 4 cells have to add up to 1. So there's really only 3 things that we don't know. But we only have 2 pieces of information, right? Both of the marginal distributions also have to add up to 1. So each of the marginal distributions provide us with 1 piece of information, but we have 3 unknowns. So we're stuck. That's the sad thing. So strategies in this simple binary outcome, binary treatment context for pinning down the joint distribution, you can think of them as just ways to pick one of these numbers. Right? So one thing you can do is you can say, well, based on my institutional knowledge of this treatment, I don't think the treatment makes anybody better off, or anybody worse off, I should say. That may be plausible for some treatments, not plausible for others, but if you're willing to say that the treatment doesn't make anybody better off, that means there's nobody who is employed in the control state and not employed in the treated state. Right? So under that assumption, that the treatment effect is 0 or positive, this cell's empty. And now you're done, right? You know that this is 0.6, this is 0.2, that is 0.2, right? Because it has to add up to 1. Each row has to add up to 1, each column has to add up to 1, the whole table has to add up to 1. But that rested on an assumption, right? You fill in one of those 3 pieces of information that you need when making an assumption. And then you have to make a case. Again, don't announce, motivate, defend, right? In some contexts, that may be a very reasonable assumption. In other contexts, it won't be. What I want to talk about next in this context is set identification, to use the currently fashionable term. Back when we were writing Heckman, Smith, and Clements, we just called it bounds. So it turns out that while the marginals do not point identify the joint distribution, they do actually constrain the space of feasible joint distributions. Right? So these marginals mean that not all joint distributions are possible, but many joint distributions are possible. And in fact, the literature allows you to characterize the set of feasible joint distributions by using what are called the Frechet-Hafting bounds. Excuse me. So Frechet was a French scholar writing in the middle of the century, Hafting a German scholar writing in the middle of the century. And the equations for their bounds are given here. So Pij is the probability mass in row I and column J. So if I put a 0.2 here, that says that P00 in this notation is equal to 0.2. Right? So let's talk about these two bounds, right? So there is Pij. This is the upper bound on Pij. This is the lower bound on Pij. The upper bound is very intuitive, right? It may not look intuitive the way it's written, but what this is saying in words is that the probability of any given cell cannot exceed the probability of the corresponding row and column. Okay? So if we think about this cell here, right, it has to be less than the minimum of the row and column probabilities. So this cell can't have more than 0.2 in it. Right? This cell here can't have more than 0.6, which is the minimum of 0.6 and 0.8. So that's very intuitive, right? The rows have to add up, right? These two cells have to add up to that. These two cells have to add up to that. So you can't have more than that in there. The intuition for the lower bound is a bit more subtle. I'm going to defer that for a second. But what it is here, so this is the row probability, this is column probability. So you take the max of the sum of the row and column probabilities minus 1 and 0, right? So it could turn out that the sum of the row and column probabilities, like in this cell here, is less than 1. So here that sum is 0.6. 0.6 minus 1 is minus 0.4. Obviously, probabilities have to be done between 0 and 1, so that 0 is keeping things at 0. So if you apply that simple formula to this cell here, then we know that this has to be in 0.2. Right? That's pretty useful information. I think that's gotten rid of 4/5 of the possible values of that probability. So that's not trivial, but it's not point identification. It's set identification. Any questions so far? All right, now let's think about the lower bound. And it's easier to think about the intuition of the lower bound by thinking about this cell down here, the EE cell. So the marginals for this cell are 0.8 and 0.6. 0.8 plus 0.6 minus 1 is 0.4. So this cell is then 0.4 and 0.6. Why do we need a lower bound of 0.4? The reason we need a lower bound of 0.4 is if we pick a smaller value, we're going to violate the constraint that the sum of the cell probabilities is 1. So suppose we set this to 0.2. Right? So we pick a number outside of the Frechet-Hafting bounds. Those crazy guys, we don't believe them. Then this is 0.4, so this has to add up to 0.6. This is 0.6, because this has to add up to 0.8. And now I've got 0.6 plus 0.4 plus 0.2. That's 1.2. That's too much. Right? And so the lower bound here, putting this at 0.4, means that all the mass is going to be in these three cells. That's as much as we can do, right? Split all the mass in those three cells. Questions about that? Well, that's kind of cool, right? You probably haven't seen this before, even though it was published this paper 20 years ago. I always thought this was very cool stuff. There are also Frechet-Hofting bounds for continuous distributions. Formulae there are given for the continuous case. The way I like to think about the continuous case is, as I've drawn it over here, if you think about taking the untreated outcome distribution, and I've kind of done this in a sort of empirical, loose empirical way, take the untreated observations and order them in their magnitude from the highest to the lowest. Take the treated observations and order them in magnitude from the highest to the lowest. And the joint distribution is the link between the two, right? Which treated outcome goes with which untreated outcome. One bounding distribution is the case where all the links go straight across. So I kind of gave the intuition earlier. That's the case where, in a very literal sense, if you're good at being treated, you're good at being untreated. And that is so true that the ranks are perfectly correlated. So the literature calls that case of a rank correlation of 1 between the treated outcome and the untreated outcome as rank preservation. That's the term that eventually the literature got to. We don't call it that in Heckman, Smith, and Clements. We call it perfect rank something. But I think rank preservation is earlier. So your rank, when you're treated, preserves your rank when you're untreated, is the notion. The other extreme is the case where the rank correlation is -1. And that corresponds, these two distributions correspond to the two bounding distributions. The distribution that corresponds to this, and the distribution that corresponds to that. In the other extreme, the ranks are inverted. This is the mighty are made low, and the lowly are made high, right? So the best outcome in the treated distribution corresponds to the worst outcome in the untreated distribution, and vice versa. You can see immediately that that case, where the rank preservation is -1, implies much greater treatment effect heterogeneity than the case of rank preservation, where the rank correlation is +1. Because treatment effect, again, is the difference between the treated and the untreated outcomes. If you're inverting the untreated outcome distribution and matching it up to the treated outcome distribution, the person with the best treated outcome has the worst untreated outcome. So they have a giant positive treatment effect, right? The person with the worst treated outcome has the best untreated outcome. So they have a big negative treatment effect. In contrast, if the rank correlation is equal to 1, the rank preservation case, the other bounding distribution, then the treatment effects in a relative sense are all going to be modest, because the best treated outcome corresponds to the best untreated outcome. Maybe they're different, but they're not going to be as different as the best treated outcome and the worst untreated outcome, unless the untreated outcomes are homogeneous. So that's kind of cool. So let's think about that in the context of the binary treatment and binary outcome. And I recognize that if I had greater skills at some computer graphics program, I could not have to draw this every time. But that's where I am. But those skills have actually decayed over time for me. I'm very reliant on other people to create pretty graphs for me and stuff. Okay, so I want to consider now the two bounding distributions in the 2x2 case. So the upper bound distribution, remember the bounds on this cell were 0 and 0.2. The upper bound was 0.2. So 0.2 plus 0.2 is 0.4, 0.2 plus 0, 0.2, and then this is 0.6. That's one bounding distribution. The other bounding distribution, right, remember this bound is 0 and 0.2, so the other bound is 0 on that cell. So that means that that's 0.4, that's 0.4, and that's 0.2. Right, that's all just addition. So here we have two joint distributions that correspond to this, or two joint distributions that correspond to exactly the same margin distributions. These are the two extreme joint distributions, right? One is the upper bound, one is the lower bound. Let's think about what they represent. So in this world here, nobody is made worse off by the program, it turns out. 80% of people have a treatment effect of 0 on employment. Right? 20% of people are not employed in both the treated and untreated states. 60% of people are employed in both the treated and untreated states, so their treatment effect is 0. 20% of people, and this has to be true given that we put 0 people over here, 20% of people go from being not employed in the control state to being employed in the treated state. So this is a world, this joint distribution, has very little treatment effect heterogeneity. Right? 80% of people have a treatment effect of 0. What about this world over here? In this world over here, 40% of people have a treatment effect of 0 instead of 80%. So 40% of people are employed in the treated state, not employed in the untreated state. Another 40% of people have their employment situation improved by the treatment. They go from being not employed in the control state to being employed in the treated state. But at the same time, 20% of people are made worse off by the program. They go from being employed in the untreated state to not employed in the treated state. So this is a world with substantial treatment effect heterogeneity. 60% of the people change their employment status as a result of the treatment. 40% go up, 20% go down. Both these joint distributions, again, are consistent with given marginals, yet they give you a very different perception of what this program is up to. Right? If we're in this world, it seems like we're wasting a lot of people's time. Like they, these programs cost real resources. If we know somehow in advance that 80% of people are going to have a treatment effect of 0, and we can pick out those people, we can save a lot of money. Right? Here, we have a world where we're making a lot of people better off, but we're also harming some people. Yeah, if we could focus the program somehow on those people, that would be very cool. So this is an example, right, a very simple example, but I think also a useful example of how the bounds work and how given marginals can be consistent with very different kind of underlying, what we call the micro foundations, if we want to be like macro people. Very different operation of the program underneath. Now, a priori, there's sort of no way to know. We know the marginals. Are we in that world or are we in this world? We have to make a case. There is a way, I'll get to on the next slide, to test the rank preservation assumption. So this is the case where the rank correlation is +1. All right, so in this case, that may not be obvious. See Johannes making a face. So let me Right, so this is 2, 4. Right, in this joint distribution, we have rank preservation. Right, so the ranks are very simple here because the outcome is binary. It's just 0 and 1. So when we order the outcomes for the treated units, we have 80% ones and then 20% zeros. When we order the outcomes for the untreated units, we have 60% ones and then 40% zeros. Rank preservation says that for the top 60%, right, it's 1 in the treated state and 1 in the untreated state, that those are each other's counterfactuals. Right, so that's these folks here, or NE and E. Right? The next 20% down in our rank orderings are people who are employed in the treated state and not employed in the untreated state. Right? That's those people. Right? And that's this part. Right? When we match up, there's this 20% where we have a 1 in one column and a 0 in the other column. Right? That's this part here. And then at the bottom of the distribution, there's 20% zeros, and because we're doing rank preservation, they get matched to each other, and that's that part. Okay? If we flip it, right, then we're taking this and flipping it around. Right? And so then we have that, right? So for the rank inversion case, where the rank correlation is equal to -1, again, these are the treated units, these are the untreated units, but now I've flipped the ordering of the outcomes for the treated units. So now, these are the good outcomes for the untreated units, these are the bad outcomes for the treated units, and I'm going to match those up. Right? So there's 20% of the treated units who are not employed, and they get matched to the upper end of the untreated distribution. So that's the 20% that are made worse off. That have a treatment effect of -1. At the other end, right, the bottom 40% of the untreated units get matched to 40% of the treated units. That's these folks here who are made better off, and then there's 40% in the middle, who, even though I've inverted, are employed in both states. That's that group. Yeah, that's kind of cool. Cool. So you can show formally that the variance of the treatment effects is maximized when the rank correlation is -1, right? So at the lower bound distribution, and that the variance of the treatment effects is minimized at the upper bound distribution. In both the continuous and discrete cases. That's just an old result from the mathematical statistics literature. That's pretty interesting, right? That's something, you didn't know that before, did you? And yet, the reason I think it's interesting is if you can get a lower bound, an empirical lower bound on the variance of the treatment effects, then you can test the null hypothesis of the common effect model, right? So as you have no doubt discerned, it is my view that the common effect model is almost never true. I would like to build up a body of evidence that the common effect model is almost never true. And in fact, it's very easy to do that because anytime you run an experiment or anytime you do a compelling non-experimental study, you can test formally, statistically, in a frequentist way, suppose you could gin up a Bayesian way to do this too, the null hypothesis of a zero variance in the treatment effect, right? That is the common effect model. So I think the next slide talks about that. Yes, it does. Excellent. So in the 1997 paper in Appendix E, now anybody else, this would have been a separate paper, but you know, Professor Heckman would occasionally tell us that you just want to have one idea per paper. And if you read any Heckman papers, you realize that this is an example of do as I say and not as I do. Because the typical Heckman paper has 20 ideas, of which 5 or 10 are also in other papers in different combinations and things like that. But if we were operating in a one idea per paper world, we would have taken Appendix C and made it its own paper, and we talked about that before we even do it. So I think it's underread for that reason, buried in the back. But what we talk about in Appendix E, that's a chalkboard on the other side, is kind of how to test this null. And I want to give you a little intuition about this because it also illustrates an interesting point of applied econometrics. So we know from this mathematical result that the variance of the treatment effects is minimized at one of the two bounding distributions, right? That it's minimized when you assume that there's rank preservation, that the rank correlation is equal to 1. So that's where you go do your test, right? There's no, if you can reject the null there, then you can reject it for any other rank correlation. Because you've taken the case, this is why this is empirically feasible, because you're going to look at a particular rank preservation, namely rank preservation is equal to 1. There's only one of those joint distributions. Right? There's one joint distribution of rank correlation 1. There's one joint distribution of rank correlation -1. There is an infinite number of possible distributions with rank correlation 0.2. For example, this is a point that we show in the paper. So this is nice. We're going to look over at one edge of this space, the one with the rank preservation that has the lowest possible variance of impacts consistent with the given marginal distributions. Now, think about being in that world. Suppose you actually are in a world where there's a common effect, and you've collected experimental data on this treatment that has a common effect. And you estimate the variance of the treatment effect using the data from your experiment, again, in the world where the true treatment effect is common. What's going to happen? Right? Well, let's say you've got 1,000 treated units and 1,000 untreated units from your experimental evaluation. You line their outcomes up in order. You difference the 1,000, the best treated outcome minus the best untreated outcome, the second best minus second best, third best minus third best, thousandth best minus the thousandth best. That gives you 1,000 numbers. Some of those numbers might be 0, but most of them are not going to be. We're thinking about an outcome like earnings. And then you take the variance of those differences. Right? Variance involves squaring everything, right? So the negative differences don't cancel out the positive differences. That's part of the joy of the second moment. Right? You're going to get a positive number every time. Right? So the thing that makes this interesting from an econometric standpoint is you're at the boundary of a parameter space, right? The variance is bounded at 0. You're testing parameters and testing null hypotheses at boundaries of parameter spaces, it turns out, is always a bit interesting. And the intuition here, why it's interesting, is that even in the world of the null, the test statistic is always positive. Right? Even in the world of the null, the world where there is in fact a common treatment effect, in any given data set, when you estimate the variance of the treatment effect by imposing a rank correlation equal to 1, you're going to get a positive number. Right? So you can't say, oh look, every time I get a positive number, therefore the null hypothesis must be false, because even under the null, because of random sampling, and because you're squaring differences, so they don't cancel, you're always going to get a positive number. So that's the thing that makes this a little bit challenging econometrically. So what we do is, just to get an empirically feasible and meaningful test, is that we simulate the distribution of the test statistic under the null by using the data only from the control group. Right? So we take the control group data and we draw, let's say, 1,000 observations at random. We call that the simulated treatment group. We draw another 1,000 observations at random from the control group, and we call that the control group. We impose rank preservation. We calculate the variance of the treatment effects under rank preservation. We put that number to the side. We do that over and over and over again. In each case, drawing our 1,000 faux treatment observations from the control group and 1,000 more observations from the actual control group, because we know that nobody's treated in the control group. Right? And so we know that there is a common effect when we compare our fake treatment group, drawn from the control group, to the actual control group, drawn from the control group. We know that the treatment effect is 0, right, for everybody, because we're drawing both the fake treatment group and the control group from the control group outcome distribution. So what we're doing is essentially simulating the distribution of the variance of the impacts in the world of the null, where we're creating the world of the null by drawing from the control distribution for both the treatment units and the untreated units. Is that clear? I went through that a little fast. And if you hadn't seen like the bootstrap before and things like this, this may seem a little foreign. But how does every test work? How does every classical frequent test, statistical test work? Right? Classical statistical tests work by you figure out a way to get the distribution under the null. Right? In the case of like regression coefficients in a linear model estimated by least squares, you get the distribution under the null from the central limit theorem, right, and some assumptions. And so you can just estimate what the distribution looks like, right? You estimate the sampling variance. Then you compare the observed statistic to the distribution under the null, and you ask, is it out in the tails? Okay? In the linear model estimated by OLS, we have formulae that tell us what the distribution under the null should be under various assumptions that, again, you should argue for rather than just announcing, but that's where we get the distribution under the null. In this context, we don't have those nice formulae. Right? So in this context, instead of using the OLS variance formula to get the distribution under the null, we use simulations to get the distribution under the null. This is closely akin to, but distinct from, the bootstrap, which is also using a simulation-based approximation of the null. We get the distribution of the null, then we calculate the variance of the impacts using the actual treatment group and the control group. and we say, where does that lie relative to our simulated distribution under the null? If it's in the tail, then we reject the null hypothesis of the common effect world. If it's not out in the tail, we don't reject the null hypothesis of common effect world. Yes?
Isn't this Monte Carlo simulation?
Yeah. Well, but it's not Monte Carlo simulation, because in Monte Carlo simulation, you usually explicitly say, here's the DGP.
Oh,
Right?
so you
This is
draw
an empirical
from-
simulation.
Okay.
We're drawing repeated random samples from the data, rather than writing down a DGP and then simulating the error term on top of the DGP. Right? We're not taking any stand here on the DGP. We're just drawing repeated random samples from the control group, 2 each time, one that is our faux treatment group, one that is our control group, calculating the variance of the impacts in the world of the null, until we get a distribution of the variance of impacts in the world of the null. And then we can look at whether the actual estimated variance of the impacts under rank preservation is in the tail of that distribution under the null.
But you need to have a very large data, isn't it?
You don't need to, it's better to. I mean, it's always better to have a very large data. I don't think there's any controversy about that. Yes, this works better when you have a big data set. So we did this with the adult women in the Job Training Partnership Act experimental data. And there we have several thousand treatment group members, several thousand control group members. The control group is actually smaller because they didn't use a 50-50 random assignment ratio. We do it using percentiles. We collapse both distributions to percentiles and then do this exercise. That proceeded very quickly in Fortran, which is how I wrote it in Fortran. And, seemed well behaved. Would it be better to have tens of thousands of observations? Yes. Would this work well if we had 50 observations? No, it would not. But we had a reasonably big sample in that context. So I don't understand why this doesn't happen all the time. Why people aren't always testing this null. Anytime you do an experiment, you can test the null of zero impact variance for whatever outcome you care about. It's pretty easy to do. Now maybe I should have written a Stata program, that's probably true. That's the road to citations. It's also the road to having your stuff actually used, is to write the Stata program or the R program. Didn't do that, maybe I should have. There's another idea for a student. Other questions? All right, quantile treatment effects, which are related, as you will see. So something that has caught on a little bit is quantile treatment effects. We present quantile treatment effects in the Heckman, Smith, and Clements 1997 paper. Unfortunately, I only found out years afterwards that we were not the first people to do quantile treatment effects. There's an early paper by a guy called Roger Conker at the University of Illinois that does quantile treatment effects without calling them that. So I apologize to him profusely, because I felt very guilty when I discovered that. So these go back a while. They become relatively popular. I want to make 4 points about quantile treatment effects, I guess. One point is that they relate to what we've already been talking about. So the quantile treatment effects, as is noted here, if you interpret them in one way, and we'll talk about that, are just the impacts that you get from imposing rank preservation. That's point number one. So that's the link. That's why this comes after the discussion of rank preservation, is that quantile treatment effects are just differencing across percentiles of outcome distributions. That's what you do when you assume rank preservation. Now, you can do the quantile treatment effects without assuming rank preservation. That's the second point I want to make, is that you can do quantile treatment effects and you can interpret them as if rank preservation holds, in which case they have one meaning, or you can do quantile treatment effects and interpret them as if rank preservation doesn't hold, and they have a different meaning. And I will go through that in an empirical example, so put that on the shelf for a second. I like to think about that as impacts on quantiles and impacts at quantiles. I always worry when I am presenting to an audience of non-native speakers that I am making my interpretation hinge on the difference between two English prepositions. So I will try to make the intuition clear, again, in the context of the empirical example. The third point I wanted to make is that you can actually test an implication of rank preservation. This is something that should be widely done, but is not widely done, in my view. What is the implication of rank preservation? Well, let me go to the empirical example. Talk about that too. So here's the empirical example. So this is a picture from Heckman, Smith, and Clements in 1997. So this is again data from the Job Training Partnership Act experiment. This is again data on the adult women. So here we're calling it perfect positive dependence. That was our term for what the literature has come to call rank preservation. So the horizontal axis here is percentiles of the outcome distribution. The outcome here is earnings in the 18 months after random assignment. The vertical axis is earnings, right, or 18 months after random assignment. So what do you see? Well, the first thing you see is there's this segment at 0 that goes from the 0th percentile to about the 20th percentile. What is that? In both the treatment group and the control group, 20% of women have no earnings in the 18 months after random assignment. Since we're assuming rank preservation implicitly, or at least we're just differencing across quantiles, those women all have a treatment effect of 0. Right? Their quantile treatment effect is 0 because the 5th percentile of both distributions is 0. The 10th percentile of both distributions is 0. The 15th percentile of both distributions is 0. And the 20th percentile of both distributions is 0. So all these things, 0 minus 0 is 0. Then we have a long range from about the 25th percentile to about the 90th percentile, or even the 95th, that's about 800. This surprised us, right? So if you're willing to assume rank preservation, then the common effect model actually seems reasonable for about 80% of the distribution, right? It's around 800. And then there's this jump up at the end. Everybody happy with where these numbers come from? Now let me talk about the two interpretations of these numbers. If we assume rank preservation, then what this says is that the impacts for people, impacts on people in the lower 20% of the control outcome distribution are 0. Right? If we assume rank preservation, then we're willing to say that the 20th percentile of the treated outcome distribution is the counterfactual for the 20th percentile of the control outcome distribution. Similarly, we're willing to say that the median of the treated outcome distribution is the counterfactual for the median of the control distribution. And that difference is 800, so that the treatment effect on someone at the median of the control outcome distribution is 800. Right? Is given by the difference between their outcome and the person at the median of the treatment group outcome. Right? That's impacts at, that's impacts on, impacts on rather than at. If we're going to assume rank preservation, then we get impacts for specific people, right? We've pinned down the joint distribution, and so we can say for each untreated person, here's what your impact is. It's the corresponding quantile of the treated outcome. It's the difference between your outcome and the outcome at the corresponding quantile of the treated outcome distribution. But we can make this graph, and it can be interesting, even if we're not willing to assume rank preservation. Right? It's still telling us something more than we get out of just a comparison of means. Right? It's telling us that this program increased inequality. Right? That's kind of interesting. We might want to know that. And we get that without assuming anything about rank preservation. Right? Because we learn that the outcome distribution of the treated units is spread out. Right? There's still this mass point at 0 in both the treated and untreated outcome world. But the outcome distribution in the for the treated units is spread out. Right? The tail goes out farther. So we've increased inequality. That just requires the marginals. Right? We're differencing the marginals here, the percentiles of the marginals. It only requires the marginals to make that interpretation. That interpretation is still interesting. Right? This figure these quantile treatment effects tell us something interesting about the program, even if we don't assume rank preservation. If you want to assume rank preservation, right, then I think, this is STEAM again, don't just announce that you're assuming rank preservation, make a case for rank preservation, right? There's a couple ways to think about making a case like that. A case that we make in the paper itself is we say, well, look, these are women in their 20s and 30s. This is a fairly short program. Probably it's not going to have life-changing effects for most people, right? They are what they are. They have some skills from high school. They have some skills maybe from a little bit of community college. We're giving them some more training. Probably that has heterogeneous effects. Probably the rank correlation isn't 1. But we argue that because the treatment is kind of small in intensity relative to the life experience of these women, that probably the rank correlation is positive and high, right? It's moving people around a bit in the ranks. It's not 1, but it's definitely positive, and probably it's 0.6, 0.7. And indeed, in unpublished versions of this paper, we had a whole kind of vaguely Bayesian setup where we defined a prior over the correlation between y1 and y0, and then we integrated the prior out, and blah, blah, blah. Anyway,
But
that all got taken out by us, I think, not the editor. Yeah.
just in terms of the magnitude, I can't really read this. So,
So it's about so this is 1,000 going
Yeah.
across. So this magnitude is about 800.
and so the difference between the how much? About $1,000 difference
Over 18 months.
over 18 months.
Yeah, $800 difference over 18 months from the 25th percentile to about the 95th percentile.
And these are the current earnings per.
These are earnings in the 18 months after random assignment.
Okay. And in the 18
Right. So
months.
this
okay.
includes the so-called lock-in period.
Uh-huh.
Right. So if you think about the standard, Becker-Minzer human capital equation, and you saw this in you didn't have the treatment group in those graphs, but it's true in the graphs that the treatment group starts out below the control group after random assignment because they're getting training.
Uh-huh.
And then after 5 or 6 months, they cross, and ultimately the average impact for the women, which is the group for which the program is most successful, is positive. You might also want to do this. You might also want to drop the first 6 months, call that the lock-in period, and just do this for the period after that. That would be interesting too. So if you wanted to push a rank preservation assumption, if you want to interpret these as treatment effects at quantiles of the untreated outcome distribution, the second thing you can do is given by this paper by Biller, Gelbach, and Hoynes. So Biller, Gelbach, and Hoynes have a sequence of very nice papers on heterogeneous treatment effects, which I highly recommend. Here, the relevant paper is the working paper version of a paper that was later published in the Journal of Public Economics. And it is a paper that takes the data from a Canadian experiment that's been used in a lot of papers called the Self-Sufficiency Project experiment, and does quantile treatment effects in the context of that program. Now, in the working paper version, they point out a test of an implication of rank preservation that I thought was very clever. It's one of these occasional moments that you will have as your careers go forward, where you read a paper and you hit yourself on the forehead and say, damn it, I could have written that paper. Right? It's one of those things where once you see it, it's completely obvious, but you didn't see it. They saw it. They wrote the paper. And so it's very frustrating, right? Other papers, the value added is they went and spent 3 years of their life gathering new data, right? This is just value added where they saw something that ex post is completely obvious. And if you had seen it, you could have written the paper. So what they realized, which we did not realize in Heckman, Smith, and Clements, and we did not realize in Jabari and Smith, is that rank preservation implies that the observed characteristics of treated and untreated units at the same percentile of the outcome distribution should be the same. Right? If I think about characteristics that are not affected by the treatment, and I believe that rank preservation is true, then the analogs of the people at the 50th percentile of the treated distribution have the same characteristics as the people at the 50th percentile of the control distribution. Right? So the rank preservation, they're the same people in some sense, right? And so they develop a formal test of covariate balance at quantiles of the outcome distribution. And if you reject covariate balance at quantiles of the outcome distribution, then you have rejected rank preservation. Now, it could still be that the rank correlation is 0.8 or 0.7. It could still be very positive, in which case probably the quantile treatment effects can be loosely interpreted as effects at points in the distribution. But it's nice, it's a test, it's evidence. And almost no one has used the test. And worse yet, the editor made them take it out as a paper. Right? It's the most important, to me, the most interesting part of the paper, much more interesting than the actual empirical analysis of the self-sufficiency project data. But the editor made them take it out. That's why I'm citing the working paper version for you, because it's in the working paper version and not in the published version. So the editorial process, I speak as a grizzled, cynical, old professor, often makes the papers better, but it doesn't always make the papers better. And you should be prepared for that. And for people who have, managed to get access to a working paper series, like the NBR, or the IZA, or the EFO, or the CEPR working paper series, you can always kind of put your director's cut in the working paper series, and then say on your webpage, you should read the working paper version because it's better. But when you're a junior person, you don't usually have access to the working paper series, and so it's harder to get people to read your preferred version. Okay, I think that's what I wanted to say about QTEs. Any other questions about QTEs? Okay, we should do more of those, that's my thought. You can see that this is both a speech to inform and a speech to persuade, as they said in my high school speech class, right? I am trying to introduce you to some literatures that you might not be familiar with, some ideas that you might not have learned about before, but I'm also trying to persuade you of some things. I'm trying to persuade you to take treatment effect heterogeneity seriously and to think about it in ways that I have thought about it. Now let's think about some more intuition. What would quantile treatment effects look like in a common effect world? What would that graph look like in a common effect world? It would be straight line. Right? Because in a common effect world, the difference up to sampling variation between quantiles of the treated and untreated outcome distributions is the same number. Right? And in fact, you can test the common effect world in a different way than I described before, and in a different way than we described in Appendix E of Heckman, Smith, and Clemens. You can test the common effect world using the QReg command in theta. Right? The QReg command, the quantile regression command in theta, will allow you to estimate models at different quantiles of the outcome distribution. You can have a treatment indicator on each of those models, and you can test for common coefficients on all those models in theta. No resampling required, blah, blah, blah. This is all I figured out much later. And indeed, we did not realize when we wrote this 1997 paper that you can get the quantile treatment effects just by running QReg from the treatment indicator, which is much easier than the Fortran programs that we wrote to do this. That was kind of embarrassing when I realized that. All right, so in a common effect world, the QTEs would be flat. What about the densities of the outcome variable? Right, so in the JGPA data, the density is, right, so for the control units, there's this big mass point at 0, and then there's kind of that, right? Looks like an earnings distribution, so it probably should be even more kind of log normal-ish. That, right? If the common effect world is true, what does the density of earnings look like in the treatment units? It looks exactly like this, but it's moved over by the common effect. Right? So if we thought that there was a common effect of 800, and this was the density of earnings in the control group, then the density of earnings in the treatment group should have a big mass point at 800. Right? From all the people going for the mass point at 0 and getting the common effect of 800. Right? It should be exactly the same distribution shifted over. That's what the common effect assumption involves. That is obviously not true. Right? I can remember sitting in the basement of the 1155 building, which is where Heckman land used to be at the University of Chicago. It's the building with the Harris School in it. One day, and just thinking about this, and having this, what seems now like a kind of trivial insight, that you can just look at the densities and see that the common effect rule has to be false. Because there's still a mass point at 0 for the treated units. That's completely inconsistent with the common effect world unless the common effect is 0. Right? Common effect world, wrong. Wrong. Okay. Yeah, I'm only going to get to the first. Well, maybe we'll spend the last 10 minutes talking about the second set of lecture notes, just to try to whet your appetite to go read my recent paper. Conditional and unconditional quantile treatment effects. So these are very different. In my example here, I'm going to explain this in the context of an actual example, is a study I did with my colleague Paul Courant, who's the former provost at Michigan, actually kind of a public finance / higher education guy, really cool guy. And we were asked by the university to do something called the Michigan Medical School Salary Study. And the university is interested in whether the compensation that it provides to female professors is similar to the compensation it provides to male professors. And they have done a series of these studies, and we were actually updating a study that was done using the medical school data 10 years before. And so we had staff people as our research assistants, which was very interesting. They're very different than graduate students. And we got generously compensated for doing this. And the value added, I think, that I brought to this was to suggest that we do quantile treatment effects. So what they had done was they had run a regression using administrative data on salaries, so very high quality data on people's monetary compensation. And they regressed the salaries on some stuff, things like what department of medical school you were in. Were you in being a family practice person, or were you in surgery, or were you in obstetrics and gynecology, on whether your degree was a PhD, an MD, or both, whether you were administrators get full salary bonuses, and when your degree was, what year you got your degree. Now, everybody understood that there was no possible way these were causal effects, okay? Because there was no conditioning of any sort on people's scholarly productivity, on their teaching quality, or on their service. Right? Those are the three things that professors are supposed to do: write papers, teach, and do service. None of that was in there. So the way they treated these results was that they would estimate the model, they would look at the outliers among the women, so the people with residuals that were way below the regression line, and they would send a list of those to the dean and said, you need to figure out why these people are paid so little. And if the dean investigated and discovered the person never wrote any papers, then fine, their salary stays low. If they investigate and find out that the person is doing just fine, then they get a salary bump. That's how they use the output of this study. So we said, let's do quantile treatment effects. Now, in these data, it is true that among older professors, they're mostly men. Among the younger professors in the medical school, there's quite a lot of women. And so if you look at unconditional quantiles, it looks really bad to be a woman. But that's partly because the women are all assistant professors, are mostly assistant professors, and the men are not mostly assistant professors, right? And we know that full professors get paid more than assistant professors, right? So unconditional quantiles aren't super informative here because of this historical fact that women have only come into the medical academia in the last couple of decades. So you really want to do conditional quantiles. So that's point one here is conditional and unconditional are different. Point two here is that the conditional quantile treatment effect turned out to be really interesting, right? So we're looking at the treatment effect of being female here. And again, not causal, everybody understands that. There's some idea that in the future they might try to condition on research output. The Berkeley salary study tries to condition on research output for a couple departments. Michigan hasn't attempted that yet. But the conditional quantile treatment effects are still interesting. In a common effect world, again, those quantile treatment effects should all be the same. They're not, it turns out. It turns out that the treatment effect of being female is monotonically increasing with the quantile. And in fact, at the 10th percentile, the point estimate is positive. 10th percentile of the distribution, you're better off being female, although that result is not statistically different from 0. And then as you march up the conditional quantile treatment effect estimates, the advantage switches towards the men and gets increasingly bigger and becomes statistically significant around the median. So that's interesting. There's value added from doing the quantile treatment effects relative to just looking at the conditional mean difference, which is what they've done before. And the value added is that you learn that the common effect model is false. That in turn has implications for what you think the underlying behavior is that's generating the difference in the average salary, right? If your simple model, which I think is a model that some of the university people held, was just, oh, those docs, those male docs don't like women, so they pay them all less, that model is clearly false. Because the lower half of the distribution is basically the same. It's the upper half of the distribution really that's different, and the men have a longer tail. That suggests that there's something else going on, right? That suggests that perhaps the issue here is that women are better at negotiating, right? So if you think that, or probably the men are better at negotiating, or that men are more aggressive about getting outside offers, right? Well, those are very different stories than just, oh, the dean doesn't like women and so pays them all less, right? That's a story that says, well, there's sort of the lower half of the distribution. Those are people who are doing their jobs. There's basically a standard pay level for them that maybe depends on things like their department and so on. And then at the upper end, it's something else. Maybe it's this outside offer thing, maybe it's negotiating, but it's something else for which the policy prescription is probably different than if it's just a common effect over the whole distribution, right? There, if that's the world, maybe you just re-educate the dean or put in a female dean or whatever, right? If it's outside offers, that's harder. You need to think about that. Maybe you need a course for star professors in how to get outside offers. Who knows, right? But my third point here is that by doing the quantile treatment effects, we rule out one model of where the difference in the average salaries has come from, which leaves us with some other models that have different implications for what the university's response should be. Right? So this is sort of not just academically interesting, although it is academically interesting to try to sort between these models. It's also interesting in a very practical policy sense to sort between these models because the different models provide different policy responses. Yes?
In the beginning of the study, you mentioned that you had the data on year of PhD graduation for people. So, but isn't that captures the old professors thing? Like, you know, if Professor A doesn't be graduated, what's the difference?
But the unconditional quantile doesn't have that in there. Right? The unconditional quantile is just salary on dummy variable for being female at different percentiles of the distribution. When I say unconditional quantile treatment effects, that's what I mean, is Q reg, Y, D, where D is the dummy for being female. Right? When I say conditional quantile treatment effects, I mean that we've got all those X's in there that I listed. And those X's are pretty important. And indeed, the most important one is not actually age. The most important one is what department you're in. If you just run a parametric linear model estimated by least squares, the R squared of the department indicators is 0.8. Right? There's nothing else in there except the department indicator. It explains 80% of the variance in the salaries. So it really matters whether you're a surgeon or an OBGYN or something else. You know, all the rest, in some sense, is minor. But there are these important differences. Again, tiny compared to the departmental differences, but there are these important differences in the shapes of the male and female conditional distributions, with the male tail being longer. Right? That was a finding that had not come up in the study that we were repeating from 10 years before. And it's a finding that I think is of interest to the university. You know, it's of interest to me. So Paul and I are hoping this fall to write this up as a paper and send it out. an issue that the federal government got a hold of the study and decided that it constituted evidence that the university was engaged in illegal behavior. Which indeed it may be. But the problem with that is, so both Paul and I had to talk to, spend a happy hour with 4 lawyers, 2 who work for the university, 2 who work for the firm in DC that the university hired, and we had to explain how we've done all these different things. Anyway, so it's become a bit fraught. The issue is, right, that if the government goes after the university for doing a salary study, no other university is ever going to do a salary study, right? And if you stop the universities from doing salary studies, they're never going to know that the phenomenon exists, right? So it's not clear that if you care about women receiving equal compensation, that you should go after the university for doing a salary study, right? The university is gathering this evidence to try to figure out who to give raises to. But that's the federal government, being the federal government, so. Other questions about this? This is one of the more interesting things that I did in my 12 minutes in Michigan. Okay, we have 7 minutes left. Let me do 2 things. One thing I want to do is I want to mock random coefficient models, and I can do that in just a couple of minutes. So what do I mean by this? So one way to pin down the joint distribution, right? So one way to pin down the joint distribution is to assume rank preservation, right? That implies that you want to go look at quantile treatment effects. Another way to pin down the joint distribution is to assume that the treatment effects are unrelated to the untreated outcome. Right? So here's the treatment effect that's independent of the untreated outcome, given treatment status. That I'm going to call the random coefficient model. That's not really a good name, because you could have random coefficients even if this weren't true, but that's what the literature calls this. So I want to make 2 points about this. First point is there you can test this assumption. So if this is true, then we know the variance of y1, right? y1 is just y0 plus beta di. If they're independent, beta di and y0, then the variance of the sum is just the sum of the variances. Right? We can do a little tricky subtraction, and we get that the variance of the treatment effects is the difference between the variance of the treated outcome and the variance of the untreated outcome under this assumption. A test of this is whether this number is positive. Right? If this model is really false, then it could be that, in fact, the variance of y0 is bigger than the variance of y1. Now, this test has a very low power against some alternatives and very high power against other alternatives. Right? You sort of need the correlation to work in the right way between the treatment effect and y0 for this to end up negative, this difference. So it's not a great test. It probably doesn't have a lot of power, but you can test it. And indeed, for the male youth in the JGPA experiment, this estimate is negative. So for the male youth, you can reject statistically this random coefficient model that says that the treatment effects are unrelated to the untreated outcome level. That's kind of cool. Yes?
Can I ask you, how much important is to have a good set of covariates in this case? I mean, because I guess if you have many controls, you probably reduce also the variance. I mean, and you control for the heterogeneity in the different groups. And
so the covariates here would just be sucking up variance, but that's fine. That's what you want to do, right? We did this unconditionally. Maybe if we did it conditionally, we would be able to reject the null for some of the other groups. I don't know. But whenever you can suck up residual variance, that's almost always good.
Okay.
The covariates that you have in these data don't do a super good job of sucking up residual variance. But all right, so one point I wanted to make was you can test this assumption. The second point I want to make is when would you ever think this assumption was true? Right? Because this assumption, this gets back to our earlier discussion of what do units know about their treatment effect. Right? For this assumption to be true, it has to be the case that units don't select into treatment based on the treatment effect. Why would that ever be? Right? I mean, even if we think that individuals don't know anything about their treatment, they don't know much about their treatment effect, that I'm willing to believe. Can it really be right that units don't know anything about their treatment effect? Really? maybe, but you'd want to make that case. And this assumption is ubiquitous in two literatures outside of sort of labor economic treatment effects. One of them is the education treatment effect literature, where people spend a lot of time using what are called hierarchical linear models or multi-level models. And these are models which I think are very useful pedagogically, because they'll think about, we have a school, we have students, those are the two levels of the hierarchy. We have an outcome model for schools, we have an outcome model for students, we have some random coefficients on school indicators that are being explained by, blah, 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 blah. So random coefficient models are very common in the education literature, and they're very common in the IO literature, as you probably know. But I rarely see this assumption justified, right? I'm glad they're thinking about heterogeneity in treatment effects. I'm all in favor of that, as you have learned. But why would you ever think it's going to be unrelated to treatment status? And if you're going to assume it, at least make the case. That would be my thought. All right, let me use the remaining 3 minutes to advertise the second set of lecture notes. So we got about halfway through the first set of lecture notes, maybe 2/3 of the way through the first set of lecture notes. For some reason, I had this dread fear of running out of material. And so I always prepare way too many slides. Now, if any of you have ever seen my dissertation advisor talk, you might say, well, I know where you got that. But I don't think I actually got it from Jim. I think we selected into working together, in part because we're correlated on this. He'll have 150 slides for a 40-minute presentation. This was not quite that crazy. But I always worry about having, for some reason I worry that we'll end 5 minutes early and I'll have to say I don't have any more slides. But it never happens. Anyway, the other set of notes, the other set of slides, is about a literature that I really like and have written in a lot. It's a literature on so-called within-study designs. So these are designs where you have an experiment and you use the experiment as a benchmark against which to study the performance of non-experimental identification strategies and estimators. Right, so this literature starts with the famous paper by Robert Lalonde in the American Economic Review in 1986, his job market paper. He used data from an early experiment in the US called the National Supported Work Demonstration. He put together comparison groups from two standard social science data sets, so the panel study of income dynamics collected in Michigan, the current population survey that's used to generate the unemployment rate, and he subjects, right, he covers his eyes and says, suppose I didn't have the experimental control group, what would I do? I would take the experimental treatment group and use the non-experimental comparison groups, and then I would hammer them with econometrics, right? And so he does that using the econometrics that was standard at, in the early 1980s. And what he finds is that the estimates that he gets are all over the map, right? And some of them are close to the experimental estimates, and some of them are really far from the experimental estimates. And he argues that there's no way to figure out which is which. That if you didn't have the experimental data, that there's no way to figure out which of these non-experimental estimates is right and which of them is not right. And people read this paper and said, oh my God, this is horrible, right? Our stuff is rubbish, our non-experimental stuff is rubbish. The reaction was then, oh, we must do experiments. And the JTPA data that you have seen in multiple occasions today during the lecture from that experiment was a direct result of Lalonde's paper. So the Department of Labor said, oh dear, this is a problem. We really need to be doing experiments to evaluate our programs. And so they did an experimental evaluation in the late 80s and early 90s of JTPA, and you saw the data from that. In between, there's a paper by Heckman and Hutz. So this is my committee now, Lalonde, Heckman, and Hutz. There's a paper by Heckman and Hutz, very incestuous little world we're in, that takes the Lalonde setup and says, wait a minute, if you think a bit harder and work a bit harder at doing specification tests, then you can actually weed out the identification strategies that perform poorly. So they pushed back against Lalonde. Their paper is published in the Journal of the American Statistical Association. The Department of Labor paid attention to that too, and indeed, Hutz and Heckman went to the Department of Labor and presented their work to the commission that was designing the JTPA evaluation. And so that's why the JTPA evaluation also had a non-experimental component. Right? It was expensive, about $5 million to run that non-experimental component. they wanted to repeat this Lalonde exercise using better data. And so they collected this ideal comparison group at 4 of the 16 experimental sites with the idea that Jim and Joe would then write a paper that was basically Heckman and Hutz with JTPA data. They never actually wrote that paper. But it's implicit in a lot of the other JTPA papers. The Heckman, Shimura, Smith and Todd, the Heckman, Shimura and Todd, blah, blah, blah. We learned a whole lot from that. Then, and grant me 2 more minutes, then along came in the late 90s, Tahitian and Waba. So Tahitian and Waba were PhD students at Harvard. And they were working with, among others, Don Rubin. And even though they were in economics. And he got them, working with him, gave them the idea, well, let's try to get the Lalonde data and do matching. Right? Rubin is Mr. Matching in statistics. At that time, matching was basically unknown in the applied literature in economics. There's a few papers around, but basically nobody was doing it. And the supportive work data are exactly the context where you would think that matching might give you something very different than what you get out of a parametric linear model. And the reason is that the CPS comparison group and the PSID comparison group that Lalonde used, a large fraction of those comparison group observations are nothing like the treated units at all. So when you estimate a probability of treatment, propensity score, in the CPS comparison group, like 90% of the observations have propensity scores of 0. Right? They look nothing like the treated units. And so when you do matching, you ignore them. When you estimate a linear regression, they dominate the regression line because they're 90% of the data. So that's the kind of context where you would think that matching, which focuses your attention on the comparison units that look like the treated units, is going to make a difference relative to the parametric linear model. So Tahitian and Waba write their papers. They get, after they do some stuff, they get some stunningly low bias estimates. They get matching estimates that are really close to the experimental estimates. Everybody says, hallelujah, matching solves the evaluation problem, which is so wonderful because we've soured on the bivariate normal model. We've learned that you have to have an exclusion restriction. That's no fun anymore. Now we can just say PSM, and the world is saved. The next paper in the sequence after that is my paper with Petra, Smith and Todd. And what we do in our paper is we show that basically we poke their stuff in a bunch of different dimensions. The one key dimension is that they take only a subset of Lalonde's data. We show that if you take a different subset that's equally plausible, at least, that their pretty results go away. There's a whole bunch of other things you can do that make their pretty results go away. That paper is my second best cited paper, published in Journal of Econometrics. And part of our motivation there was that, well, let me not go into the detail. We can talk about that a bunch if you're interested. The final thing I want to highlight is about that sequence of papers, which is a really interesting sequence of papers to read because it has a lot to say about the relative importance of data quality versus applied econometrics, is that when Tahitian and Waba went to Lalonde for his data, he had lost the data on women. At some point, the tape had been run over or put next to a magnet or something, and so he only gave them the data on the men. And so all the subsequent papers that use supportive work data, and there's a lot of them, only look at the men. And so I managed to talk a graduate student into going back to the original data sets, which was work. That's why nobody had done it. This is a shoe leather contribution paper. We went back to the original data sets and recreated as best we could Lalonde's data on women. And so our paper is called Women of the National Supportive Work Demonstration. And it marches through and does Lalonde, Tahitian and Waba, Smith and Todd, and more recent stuff on the data from the women to see if the conclusions that Petra and I drew in our work from the men carry over for the women. Period. Thank you very much for your attention.